is at the research group, DEC-RG of the World Bank in Washington, D.C. He is probably at the bank one of the formal expert on the topic of inequality. I would also say, recognize much beyond the bank. Roy has published in some of the leading journals, including the American Economic Review. I think you have a paper forthcoming in the Journal of Economic Growth. And so Roy is a native of the Netherlands. He studied his PhD at the University of Amsterdam. He is also a vegetarian butcher son. One of the things when I came to Kuala one of the things that I really noticed is that people here measure distances even inside the city center as minutes by car. Roy measures the distance between cities by time by bicycle. Okay, so we're in for two very, very Dutch afternoons. So today we'll be talking about poverty mapping. Tomorrow will be more about poverty monitoring. The idea is to go in two sets for 90 minutes each. So we will start on 90 minutes. Then we will have a break, not a Dutch treat. The break is on us. We will have some coffee outside and then another set of 90 minutes. Okay, anything else? I think that's all the housekeeping we need. And I also would like to welcome our online audience. I think a lot of you are connected. So Roy, without further ado.
And also a big to all of you. Thanks for taking some time out of your schedule to spend it with me. As Tobias said, the workshop, we labeled it poverty mapping and beyond, but really the theme of today and tomorrow is going to be the use of prediction methods for poverty measurement. Today, the idea is to use prediction methods to measure poverty at a very granular level, but not at a national level, but where possible go all the way down to the municipality level. That's what is commonly referred to as poverty mapping. And then tomorrow, similar prediction methods can be used to also track poverty at a higher frequency than what official estimates, like official household survey data might allow for. So again, like with the seminar, I don't know, I see a couple of familiar faces, but since it's a rather small, intimate group, I would encourage you to just speak up whenever you have any questions. We can make this session very informal, and please don't be shy. Like, no question, every question is a good question, and I'm happy to debate. And so just take advantage of sort of us being together to pick each other's brain. How many of you, just before we start, just out of curiosity, are familiar with poverty mapping or have even been involved with poverty mapping work? Just getting a rough sense of. Okay, so this will be new to, so there's one, I see one very shyly raised hand. Okay, so this will be a new subject to most of you, which is great. So hopefully you'll learn a thing or two from this. So what are poverty maps? Now, the name suggests that it's strictly geographic, but it doesn't have to be. So the whole idea of poverty mapping work is to, as I said, use prediction methods to estimate poverty at a very granular level. Now, the most obvious application is mapping poverty at a very sort of spatially disaggregated level, right? So districts, municipalities, counties, etc. But it doesn't have to be geographic. It could also be used to explore sort of cross-sectional deficit welfare for groups of the population that would otherwise be sort of statistically invisible. Think of disabled, think of ethnic minorities, etc. Right? So where a given household survey might only give you like 100 observations for some of these population groups you might be invested in. But as if you're able to sort of reliably impute welfare in something like a population census, you might now have like tens of thousands of observations on these groups that would otherwise be sort of statistically invisible. So let me just start by giving you just a few examples of what mapping poverty would look like. So here is a map of the United States where poverty for the period 2006-2010 is evaluated down at the state level. And you can see in the US that poverty tends to be concentrated in the southern part of the United States. And I think one of the sort of primary motivations for producing poverty maps such as this, and I'll show you some more examples, is just to create awareness, right? For policymakers that are given the responsibility to make sure that everyone has equitable access to services and sort of it is, you can imagine, hugely helpful if these policymakers have access to this type of information. So if they have a sense of where the areas in need are located. If there are such states, like you may well do poverty mapping exercise only to discover that there are no clear, well-defined pockets of poverty. But if there are, it will be hugely helpful to policymakers to then target the resources accordingly. Right, so just imagine the central government, the federal government of the United States, if they want to target resources, it's helpful to know that these are the states that are arguably in bigger need of those resources. Now we can take it one step further. This is again the United States, but now evaluated at the county level, right? So the first thing you can see is that sure, here we see that poverty does vary considerably across the United States, right? You can see that poverty is much higher in the southern part of the US than it is, say, in the east and west coast and northern US. But the other thing you'll notice is that even within states, it matters a lot, right? So we know, for example, that Texas is a comparatively poor state, but within Texas, you have parts of the country that are just as well off as sort of the east and west coast and the north of the US are, right? So within Texas, there's enormous amount of variation, and similar in say Florida, in California, etc., Georgia. So there is. Yes, please go ahead.
Is it percentage of the population compared of the US or for the state?
So that's a good question. So in this case, it is within the area that is colored. It is the percentage of the population whose standard of living is below a certain poverty line.
Percentage of the state's population?
No. In this, so whatever the unit of observations of the map is, so in this case, what we're mapping is the percentage of the population within the state who is below the poverty threshold. Here, for every county, this is a county level map, it's a percentage of population within that county, right? So a very bright pocket county in Texas shows you that white pocket here can be compared to white pockets, say, around Chicago or the east and west coast, right? So you have pockets of the country, even though Texas as a whole is a state where a large percentage of population within Texas lives below the poverty line. But if we start to inspect, if we start to disaggregate, you'll see that within Texas, it varies a lot. There are pockets of Texas that are very rich, and there are pockets of Texas where we observe high levels of poverty. This is maybe also a good moment to point out that poverty can obviously be measured in a multitude of different ways. So for the most part, I'll be focusing on sort of this measure, is the percentage of the population whose income or consumption is below a certain poverty threshold. But there are other measures that have been considered, right? So poverty gap is a measure that measures sort of the extent to which people live below the poverty line, right? Because this headcount poverty measure, it doesn't look at how far, like as soon as your income falls below the poverty threshold, you're counted as a poor individual or a poor household, regardless of whether you're just below the poverty line or significantly below the poverty line. There are other measures that take sort of that into account. So the poverty gap is for example, a popular measure. It also looks at sort of the average gap that poor households, by how far poor households are below the poverty line. And there are lots of other poverty measures that one could consider. For the most part, I'll be focusing here on the percentage of people within a certain economic area whose income is below the poverty line. And so again, so here, as you can imagine, for policymakers, it would be helpful to have maps like this hanging on their walls, because now also, say, it's not just federal budget that comes into play, it's also state level budget, right? So state level budget in Texas, it would be helpful to know for policymakers there where the population in need resides within their state. It should also be noted that in this case, it's relatively straightforward to produce this map because this is derived from tax record data. right? So in rich countries like the United States, mapping poverty is a relatively straightforward exercise because sort of the IRS, the tax record, simply sort of observes the incomes of every household in the country. And so there's no prediction methods that sort of that is involved here. They simply sort of pull this data from the tax records and they can simply evaluate for every household whether their income falls below the poverty line or not. Now that's unusual. Like most countries, sort of you would not be able to sort of pull sort of income data from tax records. You would actually have to go out there and collect household income or household consumption data. And that's often not a straightforward exercise. It's rather costly to collect household income data or consumption data. Yes.
So is there an assumption that something about the location is linked to poverty? Because why do we need to map it rather than what's geographical significance of geographical information instead of just income levels, regardless of where they are? Why do we need, so is the assumption that there's some public investment that can go into these areas to lift people out of poverty?
It will be a multitude of sort of factors that are presumably responsible for that, right? It's the quality of education, it's the quality of healthcare, it is access to jobs, it is presumably some of these things will be within the control of the government, not everything. Like access to jobs is probably a mixed bag, but the US, for example, despite the fact that it's a rich country, you'll be amazed to see how the quality of education and access to education, and how the quality of healthcare and the cost of healthcare, how much variation there is in the countries. There was years ago, there was a really impressive article in the New Yorker. I don't know how many of you are familiar with the magazine, the New Yorker. They do this in-depth sort of journalistic investigative pieces. And one thing that's sort of kind of fascinating in the US compared to Europe, where I'm from the Netherlands, is that the price of healthcare varies tremendously. And consequently, the access to good healthcare, right? If healthcare is very expensive, it sort of makes it much less accessible to many people. And you might have poor households who have a sick child who sort of have to wonder whether they can afford to send their children to a doctor if it's really expensive. And so they also mapped the price of healthcare and sort of correspondingly access to healthcare at the county level. And they've noticed that even something like this varies enormously. You can have two counties sort of sitting side by side in the US, where one has very good quality healthcare at an affordable price, whereas the very next county sort of has healthcare that is much more expensive, but not necessarily sort of much better. And so some of those variables, and the same with sort of schooling. You can have the quality of schooling and sort of access to quality education can vary abruptly from one county to the next. So if you would map school quality and access to healthcare, et cetera, you probably also get like a really stark sort of geographic variation. And these are arguably some of the drivers among many other drivers. But to that extent, it would be helpful. And ideally, you would not just be mapping poverty. Ideally, you would also have a good sense of the geography of some of these determinants. And then taken all together, hopefully that will help sort of inform policymakers to develop a suitable policy agenda. Any further questions on this at this point?
So
Yes.
you're mapping, this is what you mapped?
No, this is something I pulled from the World Wide Web as just to give you an example. And the other thing I pulled, the reason why I took the US is to sort of make the point is that for countries like the United States and Denmark and the other countries in the world where this kind of information can readily be pulled from sort of records, this is a relatively low cost exercise, right? In most countries in the world, producing something like this is not a low-cost exercise, right? Because the type of data that you need here, you need to observe for the population living in something as small as a county, what their incomes are, and then correspondingly what percentage of those incomes are below. But that data is typically not very available, so you'll have to collect that data from a household survey, but then you're going to run into another challenge. A household survey is not going to be big enough, right, to evaluate poverty at the county level. A household survey for the US might contain, say, 10,000 households, or there's a big survey, 25,000 households or 50,000 households, but nowhere near enough to sort of evaluate the percentage of the population whose income is below a threshold down to the county level, right? So for most countries in the world, with very few exceptions, you'll have to involve some kind of prediction exercise, and we'll get to that in a moment. But there was another question.
Yeah, I know that the date is 2004. So
What else is,
it is the
yeah.
latest. It's the latest.
No. This is not the latest. This is just for illustrative purposes. Yeah. I'll move on.
So back to the question, in this part of the world, Southeast Asia,
Yeah.
which countries have the best politics, if you know?
The best maps define how, like, I think they're all, whichever countries develop a poverty map, they're going to be similar.
Okay, but they were standardized across more or less, or they use a
The,
similar.
the methods are highly sort of harmonized. So
They're harmonized.
yeah, it's actually, even in the early days, so this, the sort of this poverty mapping sort of, the methodological work was developed at first at the World Bank, in the research department, Pete Wanya, I don't know if you may know him well. And then, so in the early days of the poverty mapping work, the World Bank had the research team where it was developed had a big part in sort of building this problem. But from very early stage, we tried to get sort of academics and sort of people locally on board so that they can sort of develop the maps themselves. But sort of the methods that were used were very harmonized. In fact, also we developed a software to like guidelines, software, etc. We're also developed in-house, trying to make it as less costly as possible. And so most of the countries where it was developed, it was used similar sort of guidelines, similar software, similar sort of approaches.
But does Malaysia have a poverty map? I mean,
That's a good question. I don't. You may be able to answer the question better than I can.
you may not know, but it's.
Yeah. It's a good question. I'd be keen to know. That's
Yeah, if you're in Malaysia.
Yeah.
I can never plan.
I mean, there are some out there, but it's just that the data that has been used to create them are not publicly available. But there are maps of where you can look at by ethnicity, for instance.
But like down to like Malaysia, down to the municipality level, say, of Malaysia, have you seen that? Does that exist?
Yeah, maybe not at such a low level, but it does exist at an administrative tool level. Yeah.
Okay.
And do you guys use satellite imagery or nightlife?
So that's the second part of today's talk.
Oh,
Yes.
okay.
Yeah. So you're running a little bit ahead of schedule. But yeah, so the second half of this talk, if you're around the Puva, after the coffee break, we'll discuss exactly that.
Okay. Sorry, no, I won't be around. Really appreciate it.
Yeah, so we'll get to his question later today. So this is give you an example of the country. So this is the country Ecuador. When I mentioned that sort of Pete Wanya, he was a colleague of mine in the research department. He was among the first to get involved in this to develop sort of the method. Because I said in most countries, what you'll have to do is you'll have to collect household income and consumption data. Those surveys, however, are typically way too small to facilitate really high level of disaggregation. So ultimately, the challenge would be you'd have to train a model in the household income and consumption survey data, right? So you figure out the relationship between household income and household poverty and a set of sort of correlates of poverty, and then sort of bring that model to a data set that provides you with complete coverage of the country, predict sort of poverty or some poverty into that data set that provides with coverage, and the population census is the sort of that data set that was used primarily for that purpose. And then once you have predicted household income consumption for every household inside the population census, you can aggregate it up to, say, the district, province, municipality level. And so that's what they did in Ecuador. And also here, again, you can see that even at the regional level, you observe stark differences in poverty in Ecuador. But again, also here, within those poorer regions, you'll find pockets of the country where people are just as well off as they are in the richer provinces. So this poverty maps have now been developed, probably like close to 100 countries worldwide, ever since this was the very first map that was developed with the help of the bank's research department. But by now, it's probably close to 100 countries have a poverty map. And that's a general pattern that we see, sort of as there's huge geographical, even every time you go a step closer, right, for regional provinces, you notice big differences. But even within provinces, you see really significant variation. And in fact, as countries grow richer, that sort of geographic variation, if anything, gets more accentuated. Sorry, there was a question.
No, I was just wondering now, given even for these, I don't know, like these maps, if at the end of the day you require household income or consumption data, right? For instance, has there been no attempts, for instance, to take the DHS and use, say, asset indices and then predict what would be poverty? Then you would have harmonizable, already available data sets for lots of countries, no?
I'll say
Something on that.
hold that thought because I'm going to get to it.
Okay.
Actually, yeah, I'm actually going to go to DHS in the next map, and I'll say a few more things about the use of asset indices after that. One more map before we get on map. It's the case of Vietnam, and the point we're trying to make here. So here, again, you can see that poverty shows enormous amount of variation, sort of at this very granular level, right? But the other thing the point I'm trying to make here is that on the left, we evaluate for every municipality the percentage of the population that lives below a poverty threshold. But it doesn't tell you how many poor people live there, right? Because you then have to combine sort of the percentage of people with population density. And so what we show on this map here, it is the density of poor people, like the number of poor people that by location. And you see it's almost the mirror image of poverty, right? And that's relevant for policymakers because depending on the decision-making context that the policymaker starts with, in some cases, the interest may be to evaluate the percentage of poor, but in other cases, there may be value in sort of where the number of, if you want to reach as many poor people as possible, you might want to prioritize areas where the density of poor is equally high. Now, this is a map where the DHS comes into play. It doesn't have to be poverty that we're mapping, right? So what we're mapping here, for example, is malnutrition, stunting prevalence. So here, again, the method is the same. So with poverty mapping, the map of Ecuador and Vietnam, there is a household consumption survey. You train a model where household consumption is your dependent variable. Regress on a whole set of sort of strong correlates, demographics, education, employment, asset ownership, dwelling characteristics, community characteristics, etc. In this case, the framework and the approach is exactly the same, but now instead of having household consumption and household income as the dependent variable, it's child malnutrition indicators, child wasting, child stunting, etc. that are the dependent variable. One sort of stylized aspect that has emerged from this type of work is that it is found to be the goodness of fit of these empirical models, right? That are being trained on a survey and then sort of brought to the, in this case, population census to predict out of sample. The goodness of fit of these malnutrition models is much lower. Than it turns out it's much easier to predict household income levels than it is to predict child health indicators.
And is this because of outliers like India, or this is within any country?
Within the country. So this has been done in Nepal, it has been done in Cambodia, it has been done in Morocco. I can give you like a whole number of countries consistently across the board. It doesn't really matter what country you look at. It turns out it's much harder to predict child health indicators than it is to predict household.
And the possible reasons for that?
I think so. It suggests that sort of there are a lot of unobservables that are very like hygiene practices and sort of access to sort of
intergenerational malnutrition takes time to cure.
Parental knowledge. I mean, I think there are probably a lot of factors that are hugely important for sort of child health that we simply don't observe in your typical life. What do we observe is household size, education of the parents, age distribution of the parents, whether they work or not, some dwelling characteristics, some asset ownership, community variables. What you don't observe is hygiene practices, the prevalence of other diseases in the direct vicinity, whether water is infected or not. Like there are a lot of variables that are presumably hugely important for sort of these child health indicators that are typically not observed in sort of household survey data. But I'm speculating here, so don't quote me on it.
Yeah. So you show that the type, the measure can completely change the map. So it could be to proportion of population versus density.
Yeah,
Now, of course, the remedy has to be linked to whether we're looking at density or, so what do you think is a right way, but in terms of public access, like access to public goods? Is proportion the right measure of, because it has to vary of what we are.
I don't think there is a universal right or wrong measure. I think it's going to depend on the decision maker sort of context. And so for one policy, the policymaker would be more helped by knowing where the number of poor are located, whereas in another policy intervention, it might be helpful to know what the, sorry, I interrupt.
No, I'm just saying that, for example, if you look at policy, that could guide to the measure that we're looking at. So let's say cash transfer, of course, it should go to where there's more poor people, but let's say public policy, like education and availability of schools and infrastructure, that seems, I mean, that's my sense that the policy measure or the policy action that, or policy instrument that you're looking at must guide the measure that you're, poverty measure that you.
Sure, for sure, yeah. And in practice, what you see is that policymakers do tend to prioritize, as you might expect, sort of areas where there's the higher concentration of poor people. And so what you do tend to see is that as countries sort of alleviate poverty, there is first the poor in the more accessible, higher population density areas where poverty is reduced. And then Vietnam is a good example of that. And then over time, it is those more remote places where poverty is found to be a highly persistent sort of phenomena, right? Those where presumably it's also more expensive to sort of help those households sort of climb out of poverty. But poverty transfers, we'll get to that. So actually, so what are some of the reasons why policymakers may want to have a poverty map? So one, as I already mentioned at the outset, it is just, first of all, it just creates awareness. I think it's very helpful to know. Ideally, you want policymakers to have sort of a poverty map of their country of interest hanging on the wall, because I think it's very good to know where sort of pockets of poverty are located in the country and where sort of the needs are. And as I already mentioned before, there's also growing empirical evidence that suggests that even as countries go richer, that's these spatial disparities are not going. If anything, they get bigger. I just showed you the US, right? That's presumably a very rich country, and even in the US, you see that those sort of this variation in local poverty levels. If anything, they go starker. Poverty, you mentioned targeting resources, cash transfers, etc. Right? That is a very obvious application. Just think of, and I think it might be on the second slide, but I might as well mention it here. Think of what is a popular policy interventions across the world now is for countries that are heavily subsidized. Think of fuel subsidies, right? So fuel subsidies is physically very expensive, and I think Malaysia might have considered it. Egypt is a big. There's a lot of countries in the world where fuel subsidies, where fuel and other commodities, like in Egypt, for example, bread is also heavily subsidized. It's usually expensive. It's very regressive. A lot of fuel subsidies ends up in the pockets of the rich, and it's not fiscally sustainable. So sooner or later, countries will try to sort of unwind those fuel subsidies. But then the question is, sure, even though these fuel subsidies were disproportionately consumed by the rich, doesn't mean that the poor were still dependent on them. And so when you unwind those fuel subsidies, governments will have to pair that policy intervention with something that compensates the poor from that removal, right? So ideally, governments will want to have some kind of transfer scheme that will soften the interventions for poor households. Now, to that end, especially in countries where we don't simply have a IRS or a registry that will tell us exactly where every poor person lives, right? Having something like a poverty map can be very useful. Sort of, if you want to target sort of those cash transfers to compensate the poor following something like subsidy removal. Speaking of awareness, if you have multiple poverty maps over time, it's also usually helpful to know where the persistently lagging areas are, right? So it's one thing if at any given point in time there are pockets of poverty, but if you see that multiple periods in a row, there are these pockets of poverty in the country that where poverty is extremely persistent and sort of there's no lack of development, I think I think it's important to create awareness of that, and it's important to put that on the radar of policymakers. And so decentralization, I mentioned the US as an example, right? So for federal government, it's helpful to know how poverty is distributed across states, and they allocate resources across states. But within states, right, it is helpful for even state governments to know that within the state, sort of how is welfare distributed. So I mentioned already that poverty maps have also been used to make statistically visible groups visible, disability, ethnic minorities, etc. And I mentioned this one already. Yes, please.
Is this any this variation in local poverty levels could be used also as a measure of inequality in
Spatial inequality? Yeah,
okay.
for sure.
And I mean, it does it it does do a better job than other measures of inequality, or?
Well, it's a component of inequality, right? So what is routinely done in sort of inequality studies? I just saw a presentation on inequality in India not too long ago, where people do between group inequality decompositions, right? So you can imagine that for, say, Malaysia, you can measure income inequality for the country at large, but that can then be decomposed, right? Just if you use a decomposable measure such as, let's say, the mean log deviation, which is perfectly subgroup decomposable, you can write total income inequality in Malaysia as a sum of between group inequality plus within group inequality. And I think there was a workshop here on Monday where that was done for Malaysia, right? And so, but those groups, they don't have to be geographic, right? They can be ethnic groups, they can be sort of other, but sort of having those groups be regions, provinces, municipalities is a logical choice. So then you could verify, especially if you do this repeated points over time, to what extent total inequality in Malaysia, say, is driven by widening gaps across different geographies versus inequality within, right? And sort of policy interventions may vary, whether it's mostly driven by inequality within every small geographic area, or where most of the inequality at the national level is due to differences across municipalities, say. So another sort of, speaking of targeting resources, so I was involved, the European Commission reached out to us some years ago. I forgot the exact year, I think it was like 2011 or so. So the European, and they asked us to build poverty maps for every new EU member state in Europe. And I think there are 10 of them, and they're listed right at the top of this slide. And so the European Commission, European Parliament, have a huge amount of resources. At that point in time, it was something like 350 billion euros. And the whole purpose of that amount of money was to invest it in the lagging sort of areas within Europe. And to facilitate, so you mentioned spatial inequality, this is exactly what Europe was interested in. So Europe is interested in reducing spatial inequality. So they want to identify the lagging areas within Europe and then try to lift those lagging areas in order to sort of establish some spatial convergence. And they have this huge pot of money specifically for that purpose. The whole idea of that pot of money is to reduce spatial inequality. But to achieve that, they would need to know where are the lagging areas in Europe to begin with, right? And so they had this huge pot of money available for targeted resources. What they didn't know is where the lagging areas were located in Europe. And so they reached out to the World Bank at the time to help them build those poverty maps for these 10 European countries. Here we just plotted 6 of them, and again, it's just to give you an idea that also within Europe. So this is the level where your typical household survey is able to produce estimates. So the maps you see here are not obtained using sort of a poverty mapping sort of out of sample prediction exercise. This is the level of detail that most surveys would allow you to disaggregate your data at, right? So in every given survey, you might have a household sample of 20,000 households, and these surveys are designed in such a way that they will give you unbiased estimates down to say one level below the national level. So what you see here is strictly obtained using survey data. Here are the maps we obtained by adopting sort of poverty mapping methods. And again, you can see that there's a huge amount of geographic variation, right? So if you want to identify the real pockets of poverty within Europe, it doesn't help you to only have sort of this data. You would need to map poverty down to this much more granular level. Yes.
I was just wondering, looking at some of the countries there, what is the prevalence of nomadic poverty? They move.
Nomadic
Like-
poverty.
Yeah.
That's gonna be tricky. That will be a challenging exercise.
Because
so
these
I-
countries have got a lot of, gypsy population.
Yeah.
Right?
So I know. So I'm not the right person to ask, but I know that at the same time we were doing this project, there was a team that was specifically sort of put in place to investigate the gypsy community, and sort of the poverty and its drivers. So I know there's been a lot of work, like Hungary, for example, is a country where there was a huge issue. Romania, this is a huge issue. So I know it was a priority area, and I think that project was also funded by the European Commission. It's just I was not part of that project, so I would not be able to sort of answer your question satisfactorily. But I'm sure if you do a Google search,
the method
you'll find plenty of work on that subject.
So the method you'll be talking about later would also be able to capture this kind of.
But you would have to, you would. Yeah, I don't know how good the data is to target sort of the nomadic population. And it might vary from country. Some countries might do a bigger, more concerted effort to sort of make sure that those populations are part of data collection efforts than other countries. But I can't tell you from the top of my head which countries made those kind of exerted efforts. Okay, so this is, before we're actually going to get to the methodology, I wanted to include a little bit more on the targeting. So you brought up targeting, for example, following something like a subsidy reform, right? And so Chris Albers and his co-authors published a paper in the Journal of Development Economics in 2007, where and the whole purpose of the paper was to see how valuable is having a poverty map for targeting purposes, right? So the idea is the governments have a certain pot of money available to reduce poverty by means of simple cash transfers, right? Now, if you have absolutely no information of where the poor are located, the best you can do is just uniformly, right? So if there are X number of households in your country, you have a certain amount of money, you divide the amount of money by X, and that's a transfer you will be able to make. And that will introduce some reduction in poverty. Now, if you have poverty estimates and population data at the state level, you can now start to say, you know what, I'm going to give a bigger chunk of the budget to the state where there's more poor people located than the rich states, but then within those states, I have no further information. So within the state, again, I'm going to transfer uniformly. And then every time you do a little bit more granular, you say, you know what, now I have also information on the district level. So I'm going to bigger chunks of my budget will go to the poorer districts, but then within the district, if I have no further information, I'm going to make it for all transfers. And so they did this type of exercise at these various sort of levels of granularity to see how much more efficient can we target resources with the objective to reduce poverty if we have these more granular estimates of poverty. So I more or less sort of explained this simulation exercise to you already. Okay, I think I pretty much told you everything that is on this slide. Okay, some assumptions is that this budget that is used to sort of alleviate poverty is exogenously given. We assume that this budget can be transferred at no cost. And we also assume there's no behavioral responses. There's no people start to sort of migrate, anticipating sort of those things, right? So again, so we have we have per capita consumption denoted by YCH. So household H living in area C, they're going to be given a transfer A, and we're going to evaluate after the transfer what the level of poverty reduction that transfer has achieved. And that transfer AC is, the granularity is going to vary, right? So again, if we only have a national estimate of poverty, A is not going to vary across geography. Everyone is going to get the same transfer. If we're going to use state level poverty data, that transfer, the amount of transfer may vary across states. We have municipality level data, that transfer AC is going to take on a different value for different municipalities. Now there is the optimal transfer scheme has been worked out in a paper by Ravi Kambor, 1987, from economists from Cornell, upstate New York. One of us is moving to upstate New York. And so in a nutshell, what this optimal scheme looks like is you identify within, suppose you have district level poverty estimates, you know, for every district what a distribution of income looks like. That means that with that kind of data, you can evaluate the gradient of the poverty response relative to making a transfer there, right? So by how much will poverty be reduced if I send X number of dollars to that particular district, right? And that's going to vary, right? So depending on the income distribution, sending $10 to province A might reduce a bigger reduction in poverty than if I send the exact same of money to a different province with a different income distribution. So what the process does is for every district in the country, it evaluates this derivative, by how much poverty reduction am I able to achieve after transferring a certain amount of resources there. You identify the province where that gradient is the highest, where you get most poverty reduction for the given transfer. And then you start transferring money. And every time you transfer money, that gradient is going to change, right? So you keep transferring money until the gradient in that province or district matches the gradient of the second, the province with the second highest gradient, right? At that point, you start transferring money to both of those provinces until their gradients match the gradient of the province with the third highest gradient. So that's, in a nutshell, what sort of this optimal targeting scheme looks like that has been implemented for this.
But this gradient is kind of a very hard information to have.
No.
Right?
If you observe the income distribution,
Yeah.
you can compute it perfectly.
So by the gradient, you just mean that the transfer just pushes them about the income poverty.
Yeah.
line.
So you check. So you observe if for a given income distribution, right,
Yeah.
and a choice of poverty line, you know exactly what percentage of the household live below the poverty line. Right?
Yeah. Mhm.
Now I'm going to give households. I'm going to do a cash transfer to all the households within that province.
Yeah.
After the transfer, again, I can compute what percentage of households after the transfer now live below the poverty line. That difference is the gradient, right? I've wired X amount of dollars and poverty has dropped by a certain amount.
But that would be regressive because I would always want to pick people who are closest to the poverty line.
But you don't observe that. So all you know is that you don't know exactly. So
Who is who? Okay.
Who's
okay.
all you know is there are N number of people living in that district. You know the income distribution has a certain shape, but you don't know for every person what that income level is. You just know the distribution.
Okay.
And you assume lump sum tax
Exactly.
to the household.
Yeah. So
not to the local authority, and then they can spend it on roads or whatever.
no, exactly. Yeah. So we assume perfect efficiency. All the money makes its way to the household. There's no leakage or there's no spending the money on something else. It's just a direct cash transfer.
Yeah. Mm-hmm.
Okay, so here is the table. So they agreed on a certain amount of money, and that brings about a sort of poverty reduction. I forgot from the top of my head what that number is, but for the purpose of this exercise, you did uniform transfer, right? So this means that you're able. That's whatever that budget was. Again, you can look up the paper what that budget was. It achieves a certain amount of poverty reduction, and they do this exercise in 4 countries: Morocco, Cambodia, Madagascar, and Ecuador. And Morocco is further split into urban, rural. Okay, so that uniform transfer of a certain amount generates a certain reduction in poverty. And now what they're going to do is, you know what? I'm going to keep the total amount the same. What they keep the same is the poverty reduction. Okay, so the uniform transfer generates, say, I'm just saying 10% poverty reduction for the sake of argument, right? Now, if the objective is I want to reduce poverty by 10%, but now I'm going to utilize the fact that I also have estimates of poverty at the first administrative level. Think of it as states, okay? Utilizing that information, I'm going to try to reach the exact same reduction in poverty, but now because I have more granular data, I can target more efficiently, and so I am able to reach the same level of poverty reduction, but with less resources. Okay, so what these numbers mean here is that, for example, in Ecuador, to reach the exact same level of poverty reduction can be reached with only 76% of the original budget. And in some cases, like in Cambodia, for example, almost half, you can achieve the exact same level of poverty reduction with half the cost. And that's just at the state level. So now if you go one step further, say from state to say district, for the sake of argument, again, huge cost savings. And then all the way down to say the municipality level, right? In some cases, like 3/4, you can achieve the same level of poverty reduction at a quarter of the cost.
How did you find out these optimal transfer values through different of the RCTs, or how did you find out?
So this is a simulation exercise using the optimal transfer scheme that I just mentioned. So the poverty map gives you estimates of the income distribution in every subnational level. You decide on a poverty line, and so that's all the information you would need to compute the optimal allocation of resources across, say, the provinces, or across the districts, or across states, etc. And so if again, think of it as you've just done a fuel subsidy reform, you want to help the poor by means of direct cash transfers, it is hugely helpful, especially also making it less regressive if you have a good understanding of where the poor are located within your country. And the more granular, the better, right? The costs go from 25% discount, like a third discount, all the way down to like a 75% discount. Any further questions on why there is value in having?
I mean, of course, the size of the gain depends upon the extent of clustering that is going to be of the poor on the.
Yeah, so that's why these numbers vary, right? So the geography of poverty is going to vary a lot, and the income distributions within is going to vary a lot. And that's why these numbers are not identical across these different countries. Exactly. Okay, so we all hopefully we have established by now that there is value in producing poverty maps. Now the focus will shift towards how do we produce them. I've already sort of conveyed to you the idea in a nutshell, right? The challenge is that the official estimates of poverty in any one given country, I'm guessing Malaysia is no different, there is typically going to be some household survey, some official household survey that collects household income or household consumption data. That is used to produce or monitor sort of the percentage of poor at the national level, maybe broken down by urban, rural, and maybe sort of admin one level. That survey is typically not big enough. The sample size is too small to evaluate poverty at a very granular level. And so some other source of data is going to be required, a source of data that provides you with complete coverage of the country, that will allow you to disaggregate welfare to the province, district, to the spot level. The challenge, however, is that whatever that's complete, whatever that alternative is, typically in population census, it doesn't collect data on household income or household welfare. So that's why you have to find a way to combine these two sources of data. And this is where your question, but first, Shabbat.
So again, my question is linked to how much poverty is linked to where you live versus other characteristics like education, income. I know these are all a function of where you live, but again, this goes back to mobility as well. But the fact that when you go granular, there's more to discover variation makes me think that there's something that's other than geography that's linked to poverty.
Not really, it's just geography. It's just that you'll be amazed by how much geographical variation there still exists within counties. Like, if you're familiar with DC, for example, right? DC is, if you look at the US as a map, DC is a small geography, but within DC, we have like us, I don't know how many people have been to DC. It's cut into quadrants, northwest, southwest, northeast. You'll be amazed by how much geographical variation there is in a lot of sort of public services, access to jobs, you name it. So even though it's a tiny area, there's still huge sort of geographical differences in quality of public services, among other factors.
This makes me think
Yeah.
that there is something that's not linked to geography per se, that's impacting poverty.
But I don't think it means to be, I think you're misunderstanding. Nobody's saying it's the underlying geographical characteristics that are resulting in this poverty.
But it's more about avoiding type 2 errors that he was showing you in the previous map, saying which geographical areas have very high levels of poverty, but this could be as a result of the fact that these geographical areas have poor schools, have low education, have bad public infrastructure. It's nothing about the underlying geographical exogenous characteristics.
These are geographical characteristics, like school structure and.
No, I would say they're all endogenous outcomes. By geography, we are thinking about things that are given to you by nature. What is crop productivity? How much rainfall do you get?
Was the hours of sunshine?
We call them a policy relevant measure.
Yeah.
So yes.
No, it's going to be a combination of the two. So the geography will include factors that are maybe not in our policy, for example, access to a river or access to being located in a difficult to reach area. But geography also means things that are like quality of healthcare, quality of education, quality of infrastructure. I would also argue as part of geography that will dictate why we see the culture. Like, remember I mentioned that, I mentioned earlier in my talk, this New Yorker piece on quality and price of healthcare. I forgot to actually finish my train of thought there. So they did this really deep investigative piece, and they, as I said, at the county level, they observed this huge variation in quality and price of healthcare. Like the price of a doctor visit or an MRI scan, or you name it, really, it can double when you cross county lines. County lines, probably. These are really fine geographies. And they sort of try to investigate why is it that in such a rich country as the US, we see these really stark differences from one county to the next. And so they went down a list of candidate sort of explanations. And ultimately their conclusion was, it's culture played a huge role, like just cultural difference. One county versus the next. And so that's another thing that one could sort of research on geography, the geographic variation in culture among sort of public infrastructure, among sort of geographic features that are given. And the relative importance of those factors is, I haven't done such a study, but I go to guess it's going to vary a lot from country to country. It's going to vary a lot, I think, if you do that type of access in the United States versus Europe, where I'm from. You're going to, I think, first find that there's a lot of differences in the amount of geographic variation you go to account, but probably also the sort of the underlying determinants are going to vary from country to country. But I'm speculating here. It's a good question. You mentioned DHS data and assemblies. So population census data, which is routinely used to build these point maps, they don't include household income or household consumption, but they do include a lot of these strong sort of correlates of poverty, right? Asset ownership is one of them. Dwelling characteristics, the size of the dwelling, the type of infrastructure your dwelling has, access to internet, education levels, employment data. So there's a rich set of correlates. And in principle, you could extract what people have called asset index or wealth index, right? So you can do something like a principal component exercise. You identify ownership of a car, access to internet, good education, a number of variables that are very clearly positively associated with household standards of living. And you do something like a principal component analysis. And like Dion Silmer and Lance Pritchett have a couple of papers that sort of do exactly that sort of. They advocate for using these principal component-based measures of household welfare. Now, if you do that, there's no prediction exercise will be required, right? You can simply take your population census, you work with whatever asset indices and dwelling characteristics, etc., that the census readily provides you with. You apply your principal component analysis, and there you have it. You have your measure of, and then you agree on some kind of poverty threshold. Now, in principle, that can be done, and it has been done, but it comes with some drawbacks. In my view, and some would agree with me on that. One is that it doesn't line up with official estimates. It's a very, even though it's obviously going to be correlated with household welfare, but it's a different measure of welfare. Sort of household income or household consumption expenditure is still going to be different of that household sort of asset index. And it doesn't line up with official estimates of poverty. There is something attractive about having, like, how do I call it? Like, consistency between your poverty map and your national estimates poverty, right? So if your country uses its household income or consumption survey to monitor poverty at the national level and maybe at the urban rural level, there is something attractive about being able to use the exact same measure of welfare to compute the exact same indicator down to the province and municipality level. But then when you take that poverty map, right, and you aggregate it up, you're going to reproduce the exact same official estimates of poverty that are being released at the national and state urban rural level. And that's something you will be able to achieve with this type of poverty mapping exercise. If you combine the household survey with the population census, you can achieve exactly that. You can produce estimates of poverty down all the way down to the municipality level in such a way that you use the exact same metric of poverty that official estimates of poverty are based on. And also that when you were to aggregate them up, you reproduce the exact same official statistics at a more aggregate level. Yes.
But you're saying that in the household survey data, I have exactly the same asset, the information
Except
that I would have in the census.
yeah, so typically the household survey and the census, they share a lot of data, right? They share most of the asset ownership that sort of the census records are also available in the survey. Demographics, education data, employment data, dwelling characteristics. All by and large, most of the variables. I mean, typically the census questionnaire is going to be far shorter, right, than the questionnaire that you have available in your survey. Most of the questions that are part of the census questionnaire, you will also be able to find in the, and so all of those variables become part of your model that you then train in the survey, and after the model is trained, you bring it to the census. I was going to say something, but I lost my train of thought. Oh yeah, a big chunk of the work that is involved, however, in a typical poverty mapping exercise is not very glamorous in nature, and you'll discover if one day you're going through this type of exercise yourself, even though the type of questions and variables that are collected in the census will have a counterpart in the survey. Very often, more often than not, the questions are not identical, right? So they may both ask for education. They may both ask for employment data. They may both ask for dwelling characteristics. But if you compare the two questionnaires side by side, they're different. They use slightly different categories, slightly different way of asking things. And so a lot of time goes into putting those questionnaires side by side and trying to identify the type of variables that can be constructed in a way that provides like a one-on-one correspondence. So you have to do 3D. You have to map categories from one to the other. Okay, then you're gonna have a set of variables that at least on paper, look, they should have a one-on-one correspondence. Then you go to the data, make sure indeed that statistics sort of line up. That early stage where you compare questionnaires, construct the data, check for correspondence, you'd be surprised how much time it takes. So a big chunk of this exercise is just making sure, because if you rush that job, it's going to have a huge impact on the quality of the report, right? Because you're going to rely on the idea that you train your model in the survey, operating on the assumption that when I take that model to the census, that the right and left are perfectly compatible between the two, right? So if you rush that and you do a poor job, then sort of your estimates will ultimately be at lower quality. So what are the data requirements? Well, I mentioned you need a survey and a population census. You need to make sure that those two data sets have a rich enough set of variables in common that are sufficiently well highly correlated with household income and consumption. Ideally, you want your survey and your census to be linked at some fine geographic level, because that would also allow you to bring in location variables as part of your model. Very often, not in the early days, but increasingly more today, people also adopt third sources of data. So Uva mentioned remote sensing data, for example. So increasingly more, there are other sources of data you as a model might be able to get your hands on that if they can be merged both with the survey and the census, then sort of nothing should stop you from bringing in sort of more data to train a stronger model. And you need to say so, of course, to your large coverage. Now that is a bit of a superfluous statement in most cases, but because typically population census provides complete coverage by definition. But there are countries, I have no idea information, one of them, where yes, the population census covers everyone in the country. But A, people might only be able to get access to a sample of the census, which might then sort of create challenges. Or B, it has like a long, short form sort of questionnaire, and then you have to make some decision based on that.
And what is you're going to tell us? Maybe I'm jumping. What is sufficiently correlated? What is a good R square then, or what amount of variation?
Okay, so I won't have a slide, but I can tell you. So this is going to vary from country to country, right? Because the type of variables that the two data sets have in common is going to vary. There will be a richer set in one country than the next, and it also happens that the correlation is not good. So say demographic education may be a much stronger predictor of household income in one country than it is in the other country. My experience tends to be is that the richer the country gets, the harder it becomes to come up with like a convincing model. Right? In a poor country, if you obtain a university education or a tertiary degree, chances are that is going to be a very strong predictor. You'll be able to separate yourself in terms of sort of income success from a big chunk of the population. If you go to richer countries, not so much. Like people get a university education in history or some other social science that does not necessarily translate in a lot of earning potential. And so as countries go richer, people can afford sort of obtaining tertiary education that are not necessarily highly demanded in the labor market, right? It becomes a weaker predictor of sort of income success. But in low-income countries, education, employment, etc., are usually very strong predictors. R squares are typically like, think of somewhere between 50 and 70 something percent. Not for malnutrition. So with malnutrition, I'm actually speaker, it's not unusual to have an R square 10, 50%. But in these low consumption, low income populations, typically somewhere between 50 and 70%. And that's gonna maybe dictate also like how far you can go. Like if you happen to be in a country where that model, you're not able to achieve a really high goodness of fit, it just means that you'll have to accept that you might only be able to sort of disaggregate sort of somewhere. Whereas in countries where you have a really close fit, it might mean that you can go disaggregate a little bit lower. Any questions so far? No? Okay, so I'll just quickly run you through. I think we can do those next couple of slides quickly because I've more or less completed already in words, right? So big W is going to be the welfare measure of interest. So think of it as a headcount pointer that we're going to evaluate for every district of interest. We're going to assume like a simple sort of data generating process where household consumption of a person I in location C. This is a rich set of covariates, and even though this is a linear model, those covariates might include all kinds of participation, and typically does. So it might have like squares, interaction terms. So even though this is written as a linear model, this can be highly nonlinear simply by including sort of nonlinear transformations of variables, and which is typically done. And then to capture spatial correlation structure, right? Because even though this may be a very rich set of variables, you might not. There's still inevitably going to be some omitted variables that may leave some spatial correlation structure, right? Especially if some of these omitted variables tend to be sort of shared between the features. And so there is value in trying to capture that. And sort of what Elon and what is sort of standard in the literature is to adopt like a nested error structure. So there's going to be some location effect, and this helps solve idiosyncratic error. And then ELL were adamant that they, beyond sort of this nested error structure, made very minimal assumptions about the distribution of those items. Because bear in mind is that these distributions, because the welfare variable you're typically going to try to estimate is going to be a non-linear function of sort of these household items. If there's any non-normality, these items, capturing a non-normality will be helpful.
Okay, this C here is county.
C, yeah, location.
And we assume that this is the location for which the survey that has more information is represented. This model.
So there's some flexibility here. So for example, I just wrote in simple nested structure. Yeah, typically this will be the level at which you want to produce your estimates of poverty. But if the spatial structures take on a different shape, you could, for example, consider a situation where this C might be even more granular, right? So most of the spatial place structure might take place at a slightly more disaggregated level. You fit your model to the data, you impute it, but then you end up only aggregating up to say the district level, even though the spatial structures kept it at say 11 below the district level. So there's flexibility there.
Okay, but I mean, we have the survey.
Yeah.
The survey has a lot of information that the survey observed by, observes the outcome of the.
Yeah, the survey observed this X, this whole vector of X is available both in the survey and
the census.
Exactly.
But now you're telling me I estimate this with the random effect at the level of C, even though in the survey I'm probably not able to observe all.
Not all, a sample, exactly.
Okay.
Yeah, so you're getting at a good point. That's going to be a big chunk of this afternoon's presentation. Yeah. So in ELL, we don't. What they use is they don't actually estimate the effects, area effects. They estimate the distribution, and so they're going to be drawing this from the unconditional estimated distribution. But there's a second literature that does try to estimate these effects, and we'll get to that. And in which case, that only works in those areas that are covered by the survey. So you might end up in a mixed situation where for a subset of the country, you employ these estimated area effects, which buys you some more position for those, but it's all other districts that are not part of your survey, you won't be able to, all you can do is draw these area errors from the estimated sort of unconditional distribution. But we'll get to that. Okay, so ultimately we're interested sort of in this expected welfare measure, right? Conditional on observing this covariance X, and I'm putting all the model parameters in beta. So we have the beta, but it also has the parameters that govern the distribution of the area and household errors.
Excuse me, what is the difference between the epsilon and mu? U is saying that this is reverse the random effect, right?
So the difference between what and what?
Yes, the last term, refer to previous slide. Yes, epsilon C V. So
yeah, CI, it's CI comma. It's not a V. It's CI. It's a low resolution problem. So this is a random error that varies across locations. So it's like a location error. This is a household. So this error term varies across households. It's a household I living in location C. So this is like an idiosyncratic error term that varies across all households. This is an error term that varies across locations.
And beta stand for?
Beta is a set of regression coefficients associated. So this is a vector of X's, so demographics, education, employment, market risk, ownership, location variables, etc. And these betas are the regression coefficients on all of those explanatory variables.
But if we generalize, for example, the one to be like a measurement for welfare, okay?
So this is, for example, typically like log household consumption.
But I think, in my opinion, for per capita income is not the adequate measurement for the what you are looking for.
But you're at liberty. If you want to work with a different measure of household income, you can. You just replace this with another variable.
Because does not cover all the labels of the people or the categories.
I mean, conceptually that doesn't change. You're flexible to work with a different measure of but the idea being that this is a measure of welfare. You observe it's something you can construct in the survey, but not in a census. So you need to train the model on the basis of variables that are shared between the circuit and census. And after you have trained your model, you take the model to the census to out of sample, do a big out of sample prediction exercise. Okay, I'll try to speed up a little bit. Okay, so we're interested in working out the expected value of, say, headcount poverty, conditional on these predictors of household welfare X and knowing the model parameters. And okay, so there are two sources of error, roughly speaking, right? It is the fact that we have these error terms, right? So those X's, they predict household consumption, but not perfectly, right? There will always be some error terms. And so suppose we impute for every household in a location using this model, and we do that by, if we know the regression coefficients, right? We compute this guy for every household, and then we draw those error terms for every household, and then we aggregate up to, say, the municipality or the district level. Now, these errors will start to average out because it's not evaluating poverty in house level, but evaluating poverty at the village or city or municipality level. If that population is big enough, these errors will start to average out. But the population size is going to vary, right? Some municipalities have a bigger number of households than others. Those counties where the population comparatively small, they may not average out completely, they may still make a meaningful contribution to the statistical certainty for that particular. The other source of error is that you don't know the regression coefficient with certainty, right? You have estimates of the model parameters, you don't know with certainty, and that's what we're going to refer to as model error. Okay, so these are going to be like the two main sources of statistical certainty: model error and sort of the fact that. Now, these guys average out, so the bigger the area that we're going to estimate poverty for, right? The more we average out of errors, the smaller will be the contribution of this source of error. This guy, however, does not average out, right? So if I model error and I don't know the regression of uncertainty, it doesn't matter if I evaluate poverty for 1,000 households or 100,000 households, that won't average out. So this is a very critical sort of, source of statistical certainty. And then, so in a nutshell, sort of probably what is done to compute standard errors as well is we do this exercise, say 100 or 500 or 1,000, depending on your computational power. You bootstrap your survey, you estimate the model parameters, or if you're willing to make the assumption that sort of your regression coefficients are asymptotically normally distributed, and you draw your model parameters from the estimated distribution. You draw the errors from the estimated distributions. Okay, so now for the given simulation, small r, we're going to have like imputed household consumption for every household in the population census. Treat that one given simulation as if it was the true, right? The true data set. Just imagine we observe household consumption for every household in the census. We use the data to compute headcount poverty rates in every municipality or every district, right? So then now we have, for a given simulation, we would have estimates of poverty for each of the subnational units. We repeat that exercise, say 500 times. So now we're going to get 500 versions. We're going to get 500 poverty maps. We're going to get 500 estimates of poverty in every province, in every municipality, etc. The average across the 500 simulations is your point estimate, and the standard deviation will be your standard error. Okay, this is the method, and I'm going to refer to this as the ELR method. So this method, just for your information, so Ecuador, the map that I showed you at the beginning was the very first poverty map that was done. That was done by Chris Elmers, Jean Lagnan, and Peter Lagnan. Pete and Jean were a husband and wife. They were the first to develop this. It was done for an operational project within the World Bank. That's how the whole idea was born. And ultimately, the paper was published the Econometrica in 2003. It landed well. For those of you who are familiar with economics.
Yeah, I do that. I mean,
I finished my
Thank you. So for my measure of fit, I only work with a survey. I only simulate and then match to the survey. I don't take my parameter estimates. I go to my census and then
Census,
I
yeah, exactly. So you estimate your beta and the parameters of the errors. So once you have those estimates,
Put them.
you take that model to the census. So now you can forget about it. The survey comes into play. The survey comes to play if you want to do validation exercises, if you want to do out of sample testing, etc. But suppose you're happy with your model.
No, to find the model.
To find the model.
Find the model, I just work with a survey, or do I work with a survey? Then at each iteration, I take
I
my
guess that's
estimate.
Yeah,
I
model
take it to
selection,
the census.
So typically what people do is they would split the survey into a training part and maybe out of sample, they hold out for out of sample testing. Right, so you would implement the proper model selection sort of phase. But the entire model selection and model training takes place in the survey. Once you've fully identified your model to your satisfaction, which passes all your out of sample tests, etc., then you take that model to the census, and at that point, you forget about the survey. And then you just say 500 times that you draw the, for every set simulation, you draw the model parameters from the distribution. Either you can draw them from the asymptotic distribution, or if you are going to make that assumption, you can just bootstrap your survey, estimate, and then the point estimates on the bootstrap version of your survey become effectively a drawing on the model parameters from the distribution. Once you have the model parameters, which include the parameters that govern the distribution of the any error and the idiosyncratic error, then you draw the errors from the estimated distributions, and then you have everything to piece together the imputed log assumption for every household in the census. For a given realization, you just tweak it as if there was like observed data for every household in the census. That allows you to compute the poverty map. And that whole thing you repeat saying 500 times, that gives you 500 poverty maps. And the average is your point estimate, and the standard deviation across those 500 poverty maps become your standard errors. That's it in a nutshell.
And has somebody tried that, for instance, for few, maybe there's some countries in the world where you have census data, which also has your income and consumption data? I'll get to that.
Yeah.
So, I mean, it sounds almost like machine learning, but it is quite machine learning.
No, in fact, so machine learning is,
So what's the
expected with, but machine, there's a lot of overlap between machine learning literature and sort of your bread and butter econometrics industry.
Yeah.
For example, on the model selection part, a very commonly adopted approach is Lasso. Lasso model selection, for example, right? So there is some people who claim that it's machine learning, but you open up the standard textbook econometrics statistics. If the book is sort of detailed enough, you'll find a section on Lasso, and along with other model selection. So if you and people can, but a lot of people might also use the forest to help them sort of guide. So the model selection part, people can use full methods for machine learning, some of which are shared in econometrics and machine learning. So all of that, sure, that can be, and people adopt different, like different people have different preferences for how they want to organize them. You're completely free to sort of, there's no, like we don't offer guidance, like you should strictly adopt that sort of one, like no. And different folks, different strokes, as far as model selection goes.
Okay, so what I'm wondering, why would you not want to take the parameters, take them to the census,
Yeah.
estimate the income for each household in the census,
Predict, yeah.
and then, predict them, but then aggregate them up to, say, the state level where the survey is representative, from where I have my poverty estimate from the survey, and match some kind of minimum.
Oh, yes, definitely. Yeah, that's part of the validation. Yeah, so spot on. So typically that's part of that is part of the guidelines. So after you've completed your exercise, you cannot validate estimates of down to the level that you were aiming to, which one, but you can certainly aggregate it to levels in which the survey is representative, and then make sure that that's typically done. So, and then more often than not, if you've done your homework correctly, you'll find that things line up or that the estimates are within the progress intervals. However, if things went wrong somewhere along the way, and you discover at that point that sort of your estimates are not lining up, you might have to sort of go back and sort of figure out where things go wrong.
But you will only do it for validation. You you would want to do it here.
No, because you want to protect yourself a little bit against overfitting and sort of, it's good to tie your hands a little bit behind your back, and sort of, that's in general sort of, something you have to be on the lookout for. Overfitting is also because that set of covariates. So that's why it's good in a mobility part, be a little bit disciplined, and also sort of do like part of reserve training, part of forecasting. Because that set of covariates can easily get very rich, especially if you start to include all kinds of interactions and non-informations. And before you know it, you have this really large set of candidate variables. And if you let most selection sort of really run wild, it's easy to overfit your data, right? Because these household surveys are often not humongous in size. And so if that set of candidate covariates grows larger, 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 you're exposing yourself to a greater risk of overfitting, where you think you're fitting a good important part of the model, right? Your coefficient is significant, but you end up by pure coincidence. It just happens that your randomly created predictor correlates well with the other term. It gets selected, and then you end up predicting error in the census rather than a meaningful part of the model.
I mean, this is where machine learning, I mean, this is where virtual less some of the, let's say,
It helps you protect it from that a little bit, yeah. But
have more parsimonious.
yeah, but I would not blindly rely on it, sort of with human assistance. That's what that's what I tend to do. But I can also point to colleagues who do blindly rely on it. And I'm not going to be judgmental, like each their own.
And maybe one last, I mean, maybe I'm moving too far ahead, but if you were just interested in your poverty mapping and essentially poverty headcount, percentage of the population below certain poverty lines for each household, I want to predict the binary variable for would, I mean, have people compare this method, like what is regression-based method, to a random forest method, when I have this clear categorization?
Yeah, people have done it, yeah. It markets, the game is almost the same. So my understanding is of this machine learning literature is that these methods have been developed with applications in mind where you have like this really huge amount of data, enormous amount of covariates, and like I'm talking like millions of data points and like thousands of covariates, right? That's what these machine learning methods have been developed for. That's not the typical context, right? We're having a sample size of maybe like 10,000 households. And if you have like 100 covariates, you're a big boy. Like so it's the dimensions that not really the dimensions that from those methods will get that opportunity to shine. And so of all the applications that I see that sort of compare things like random forests, neural networks, and sort of all these other sort of machine learning approaches, compared to sort of your bread and butter also or even negatively built model, the differences are marginal. Any other questions on this?
Yeah, I have a question. So the that's right. The standard error that you get is the summation of both U and epsilon for the standard deviation.
The random error, like the statistical certainty that's baked into sort of your estimates probably, the statistical certainty will come from different sources. It comes from the randomness that's in the array errors, the randomness that are generated from the arithmetic error, and the randomness in the fact that your regression coefficients are subject to statistical uncertainty. So all three of those sort of contribute to this. So if you produce 500 multi-maps, right? And for each simulation, I draw my regression coefficient, my model coefficients from that distribution. I then draw the array errors, I draw the idiosyncratic errors. I use that to piece together imputed local consumption for every house on the census. That allows me to produce 500 versions of, say, the province of Malaysia. So for every municipality in Malaysia, say, you can have 500 estimates of poverty. The standard deviation across those 500 is your point estimate, and the magnitude of that standard error will be driven by those three components: area error, idiosyncratic error, and model error.
Thank you.
Okay, and really quick, how much time do you have on the first part?
So, I mean, we can distribute it. I don't necessarily have to finish one before we move on. So I'm flexible. We
Okay,
can.
just maybe a couple of minutes.
Yeah, so let me just close. Okay, let me just, and then we can go ahead. So this, I'm just going to quickly close it here. So this is just for those of you who are interested in like the nitty-gritty, just going to quickly walk through the exact steps that some are going. So in every simulation step, typically what one does is one, and this is the software. So we have developed software within the domain to make just to help make this more user friendly. This whole mapping approach. So under the hood, what it would do is it would bootstrap the survey for any given so simulated application, estimate the parameters using OLS. It would extract the total residuals, right? Because all you can do is observe the total, not observe the individual, any error, any household, all you observe is the total. You will do a nested error decomposition into any error, and you estimate the variance of the area error and the household significant error. Then EL also allows for heteroscedasticity, but I'm going to abstract away from that just for easy recognition. Once you've estimated, or once you have your OLS estimate, that allows you to extract residuals, that then allows you to do decomposition of the total error into area error effect and the household error effect, and you have the essence of the variance, each of those two. You can now piece together the variance covariance matrix of your item that reflects that spatial correlation structure. Once you have that, you can re-estimate your regression coefficient using generalizing squares, which is in effect the maximum likelihood estimator of the model parameters. And once you have that, once you have your generalized squared estimate of beta, you have the estimate of the parameters that govern the distribution of epsilon and to the area effect. What ELA does, because you bootstrap the survey at the start, the GLS estimate for that particular round is effectively a draw of beta from its estimated distribution, right? If the survey is big, that's going to be the same as drawing from asymptotic normal distribution. So it's finite sample consideration become micro. It draws the errors from the empirical distribution because it wants to respect the fact that errors may have. It doesn't want to impose normality. Because typically, if you do this type of exercise and you will inspect residuals, you'll see that more often than not, the distribution will deviate from normality. And because of the welfare measure, the poverty head count, along with other measures of welfare you might get, are nonlinear functions of household consumption, and by extension, a nonlinear function of those error terms. It is important that you to the extent there is a significant deviation from normality, you want to get that right, because otherwise you're going to introduce a bias in your estimates of poverty or inequality. So what they do is they implement a non-parametric strategy here, where these residuals are just drawn from the empirical distributions, right? So they've decomposed the total error into like estimates of the household, the area errors and the household specific errors, and then with equal probability, they just draw from these empirical residuals, right? So this will respect the shape of whatever distribution the data offers you. And then you do that once you have drawn these error terms, you have an estimate of the beta here for your particular simulation R. You piece this together, you produce a poverty map by aggregating these imputed poverty rates to the municipality level, say with this particular province level, that gives you, say, 500 poverty maps. And I told you before, you just take the average and standard deviation with any point estimates instead of this. I think this might be a moment to take a quick coffee break, and then I'll go to validation. Somebody mentioned validation. Was it?
Yeah.
Was it you? Or I forgot. Or maybe both of you together.
Different continent.
Okay, thank you. Then I hope that coffee break is already, everything should be outside now. So it'd be convenient.
Can I just say, if you guys feel like I'm going too slow, I can speed things up, but you give me feedback. If you feel like it's the right pace, or if you feel like I can speed things up, I can do it either way. But just let me know.
Okay, so it'd be convenient like 25, 26 minutes. 30 minutes past the hour.
我带我的卷子来。So only which one?
Yeah, that's why I did ask you.
Luckily, my supervisor is not. Which one? You think so?
Yeah.
Sorry.
Yeah.
Yeah, yeah. That's when you mark it. That's what I want to get. Switched off.
Strategy, the exact same way as you would in any other country where income is not part of the census. Build your poverty map. But now we actually, and the problem is derived from the same income question, right? So the income question is there. And what you would do is you would draw like a survey, you draw your own survey from that census in a way that mimics sort of what an official household survey might look like in that country, using the same definition of income. But once you've drawn your survey with that particular income question, then in the census you're going to ignore that income. You're just going to build your poverty map the same way you would in any other country where this income data is not available. Build your poverty map. And all the way to the end, after you have your municipality level poverty estimates, now you come to compare the true poverty rate that you can in principle construct using the income data that is very dynamic. And now you're in a unique position where you can sort of compare the correspondence in estimated poverty headcount rates and observed poverty headcount rates at the small area level, which is very rare that you're able to do. I can only think of 2 countries where the census includes it, and then I can think of at least 2 other countries where something similar can be done. I'll mention those as well in a short while. Yes.
But did they also compare how because in the census is just essentially a simple question, right? Like, what is your household?
Exactly. Yeah.
So as part of the exercise, did they also look at this and compare it to the more detailed income data from the?
Not in this study. In this study, they basically is purely a test of the methodology, and they use the income measure that is in the census. They draw a fake survey out of the census using the exact same data. So that you can, by construction, be comparing against the exact same measure of income poverty to allow for a clean, right? Because now if you're going to get discrepancies, it's purely because of the method. So I say if you're going to compare it to another survey where it has its own different measure of income, you're not quite sure it's because of the something off with the prediction method, or is it because it involves a different measure of income, right? It's hard to pin down what the source of the discrepancy comes from. So in this case, because both the fake survey and the census adopt the exact same measure of income, if we're going to get a discrepancy here, it's because of the messed up sample modeling exercise. There's nothing else responsible for any discrepancy here. Okay, so it's a unique set, as I mentioned. And it's a huge data set. This was done years ago, this exercise. It's published in a working paper by Chris Albert, Lanyao, and Philippe Leiter. Computational infrastructure was a bit more limited back in those days. So, and census data are huge. Like in handling census data, its data can be rather challenging. So what they did for the purpose of action, they focused on one of the largest states in Brazil, in Ceará, which is home to a lot of geographical variation. Some people refer to it as Brazil within Brazil, and in fact, I think that's the title of the paper, Brazil within Brazil. This is Venezuela, and this plots per capita income as observed in the census. So these numbers here are basically observed income data. And as you can see, there's huge variation within that one state. Higher numbers means higher levels. So these are the richer part of the state. This is infant mortality rates for Venezuela, also at a very granular level, and you can see the remarkable sort of population, right? So the high income, those sort of municipalities with high levels of per capita income are the areas where we see low levels of infant mortality rates. It's almost like you're looking at the mirror image of but they plot very different things. One plots per capita income, the other plots infant mortality. This is life expectancy for adults. Again, it's a remarkable sort of correspondence between those. So this only goes to show you that sort of anyway, so this is just to familiarize yourself with Venezuela and its sort of geography of standard of living. So what they do is they draw 41 times a fake survey from Brazil, and Brazil has two very well-known household surveys, the Panache and another survey where I forgot the name. And so what they do is they mimic. They ask the help of the Bureau of Statistics in Brazil at the time, and basically they ask the exact sort of sample design framework that was used to draw the surveys, and they try to mimic it as closely as possible. So they're getting sort of 21 times, I think, they draw the Panache, and sort of 20 times they draw this other sort of well-known for the exact same sample design as what sort of these surveys adopt. So the only difference being that now the income measure in that fake survey is the income measure that is also available. But other than that, sort of it for all practical purposes, it mimics the exact same those surveys. And then it uses those fake surveys to carry out the exact covenant procedure that I explained to you before the coffee break. And then the question is, after we use coffee maps, how well do our estimates of headcount income poverty compare at the municipal level? Given that we now have two estimates of poverty. So this is what that scatter plot shows you. So this is the poverty rate observed in the census using the actual observed income data. And this is the poverty rates that are predicted using this sort of small area estimation technique. The size of the dot is the population size of the small area. So municipality, right? So municipality will vary in population size, some are bigger, some are larger. And recall that you would expect poverty rates to be less precise for small places, in part because the idiosyncratic error and error don't average out effectively as they would in very populated areas, right? So you would expect to see more statistical uncertainty in very less populated areas. And that's what we see. But for the most part, those big dots sort of line up very nicely to the extent that poverty estimates sort of deviate from this 45-degree line. By and large, it's at really tiny places where there is going to be larger sort of statistical uncertainty because these characters typically don't average out. But by and large, this shows you that there is a very close correspondence between poverty estimates obtained through this poverty mapping exercise versus those that are obtained with observed income data. Any questions on this? Here they have a similar graph where I forgot what the unit of observation is. This might be provinces, where they check how often does the true poverty rate fall within the 95% buffers. So this is Brazil. So remember that earlier in the presentation I told you that the European Commission had reached out to us for this massive sort of poverty mapping project. By the way, that was really massive. It took us like 2 years to put the whole thing together. A lot of time went into securing the census data, and to be amazed how involved in itself the population census data is among the most sensitive sources of data that any country has. And it's not something you can simply walk into a country and say, hey, can I populate this because of this exercise I want to do. It's a long process that involves a lot of relationship building, setting up.
Even with the cover of EU,
Huh?
even when EU is behind you as well.
It doesn't matter who's behind you. Like it's often extremely difficult. And the other thing I worked, well, there's something I worked because by the time before I started this project, I was a core team member of the project. I had done quite a few pop-ups myself already in the developing world. This was the first time I did an exercise like this in sort of emerging higher income countries. If anything, I've learned that the richer the country, the more problematic it is to get lawyers get involved, sort of the memorandum of understanding become that much more complicated, which is also when you look at the rollback itself can be very peculiar, because the lawyers at the countryside want it to be this shape or form, and the lawyers at the bank say, no, there's no way we can do that. Trying to sort of bridge those two can be a daunting task, I tell you. So in many countries, it took almost like a year just to get access to the data. Many iterations on the contract and the memorandum of understanding, etc., etc. In some countries, you just literally have to walk into the building, empty your pockets in a little locker room, get into like this really secure room, as if you're in the CIA. Do your analysis. There's on computers that have no pockets, you can put nothing in, and then you finish your analysis. You can produce a table, and then you leave the room. Somebody from the settlement will go in, get the table from you, and email it out. Like a very secure sort of facility. It's so anyway. This to say that census data is a very precious data set in most countries, and securing access to it is not a trivial matter. The European Union said, okay, before you start with stuff, we want you to convince us that this is a solid sort of method. So they gave us the opportunity to test the method in 2 European countries that provide a similar setup in Brazil. So it's not quite population census, but Slovenia and Denmark use registers. So they don't do population census anymore. Like everyone is on the register. The moment you're born, you enter the register, you get a personal identification number, and all the data that's collected by the government gets linked to records. So and so at any point in time, Denmark can push a button and it basically produces census from the spot with enormous set of values, and the same is Slovenia. And so we managed to secure through that project access to Danish and Slovenian registry data. And for all practical purposes, it means it's the same type of setup as we had in Brazil. So we have now the census for those 2 countries, where we observe the same type of covariance as you, but also now we observe the income data for every year. And now this is a high quality income data. It is not like a one-shot. No, this is actual income data as observed by the Danish government through the tax records, etc. And the same for Slovenia.
Surprising that there are not more papers about Slovenia than given how people have leveraged the Scandinavian countries.
So it's not easy to get access to this data.
Okay.
So we managed to secure access through this project, but access is very privileged to this type of data. And expensive. Like it was not free. Okay, so first Slovenia. It's a small country. Actually, Denmark is not all that big either. So it's nothing like what we saw in Brazil. It's the same exercise, but on a slightly smaller scale. That's not to say there's still, despite the small scale, there's still plenty of scope for geographical sort of variation, as you'll see. And the go-to survey for measuring income in Europe is called the EU Silk. I don't know if you're familiar with Europe. And so here we drew synthetic surveys from this registry / population, trying to mimic the survey design of the EU Silk. We drew a sample size that matches exactly, including sample size, the EU Silk, and we end up using poverty estimates for 195 municipalities in Slovenia. And this is sort of the result. I'll jump straight to the result. So on the bottom, we see the true poverty rates as observed in the income registry. And on the chart in the top, we observe the poverty estimates that were obtained using the ELL approach, where we completely ignore the income data that's included in the registry. And you'll be hard pressed to sort of tell those 2 graphs part. You will see that if you were to do a scatter plot, again, as in Brazil, you're going to find municipalities, most notably the smaller municipalities, where you may observe differences. But by and large, as far as the geography of poverty is concerned, so this poverty mapping exercise does a pretty good job in recovering that geography of poverty. You agree? It's not
Looks like an estimated variation.
Yeah.
To choose much more dispersed than the estimated one.
Yeah.
It's more spatial inequality.
It is often harder to sort of, you're gonna get some, you might get some of it, like picking up real outliers. You would expect, to the extent that they're different, you would expect something like that to happen. So the really unique places might be harder to pick up. So Denmark, same setup. This is a country of 5.5 million people, about 2.5 million households. Again, we mimic the EU silk that is conducted by Denmark. In this case, that means a sample size of just below 6,000 households. And Denmark is home to 107 municipalities, so smaller than Slovenia, as far as municipalities goes. And this is the map. So it's a little bit less geographically diverse than what we saw. So other countries I showed you. Nevertheless, this is the truth. You do have pockets of poverty, but especially inequality is less in Denmark than it is in many other countries in the world. And also here, Gilal does a reasonably good job on picking up on the report. So this was at least convincing enough to the European Commission, because up to this point we hadn't gotten the contract yet. So after we sort of delivered this financial study, that's when they formally signed the contract was, and that's when they trusted us with getting out of this massive 2-year-long project. Yes.
So here you have the actual census, but for countries where you don't have, and for the method that we discussed before the break, is usually with surveys, getting the details is a problem. Is this a big concern?
I think that lines up with the point that Toby is making, right? So yeah, to the extent that there will be areas where it's harder to get it right, it's most likely to be the case, right? So places that are very unique, especially if they end up in the tails for variables that you don't observe. These will be the places where it's hardest.
But in developing countries, even census don't capture it.
There's no separate method. So you
I'm saying that's the extent of the problem.
so if the second problem is that it's already in,
Is a long shot, I think. Even census exercise is hard to do especially the bottom.
Yeah, but again, that will affect the trading of the bottom line, right? Because once you go to the census and you predict income or consumption pattern of the census, it's the census that will provide you the coverage. But it does also concern the trading of the model, because like really poor areas, right? They may be poor or income below for reasons that you simply don't pick up on all the variables that make these places uniquely poor or uniquely rich. In fact, it's rich. So if the same method has also been used to map inequality at the local level, and as you may have guessed, for the reasons you have, it's a little bit harder. Like those tend to be particularly undercovered is the rich. Any household survey, it's very unusual to have rich people that they tend to be happily uncovered. Rich people, first of all, the really rich typically are located in the top 1% of the country, right? So just if you're separate 10,000, you throwing people from the top 1% in and of itself is small. On top of it, they tend to not perform, right? They have high security costs, their time is valuable. And so even if you do by sheer luck draw some people from top 1%, more often than not, they simply won't. So that's hugely important income inequality. Like it's less of a problem for headcount poverty. If you're interested in measuring the percent of population with income not offline, missing the top 1% of the population is no big deal. But if you want to estimate the Gini coefficient for a country, that's probably the most important part of the income distribution, right? So not observing the top 1% is going to hugely bias your estimate. That's precisely, it's a little bit of digression, but if you forget this is precisely why what motivated work with Thomas Piketty. And I know if any of you are familiar with his work. right? So he acknowledges, and this is not just for developing countries, this is just as much a problem for the US, for France, UK, pretty much any country in the world. The rich are not covered in household income surveys. That the type of survey that underlie official estimates of poverty. And so what Dr. Piketty sort of ended up doing is, you know what, let me find another data source that gives me very good coverage of the rich. It may give me very imperfect coverage of the bottom, say 80% of the country. I don't care because I have the household survey for that part of the population. But I want to get it. It's a tax record data, especially high income, US, France, UK, etc. Like tax record data gives you a very good idea of what happens in the top 1% or the top 10% of a country. It may give you patchy data in the bottom 20%, but that's okay if you have the survey for that. And so he ends up combining it. So he uses tax record data to estimate the upper tail of the income distribution. He uses the survey to estimate, say, the bottom 90% of the income distribution. Then he glues it together to paint the complete picture of the income distribution. And when you do that, you'll notice even for the US and France and UK and Germany, you get a huge upward adjustment in estimates of income ability. Now they launched this website, WIID or the WID, WID, forgot which location, and I forgot which direction they changed it. At some point, an I get edited removed. So they're now on a mission of providing complete coverage on sort of income inequality estimates across the world. So it started with the rich countries where this tax record data is more readily available. But it's more readily, it still requires privileged access. So it takes people like Thomas Piketty and Muschek in the US to share access to this type of data. It's not like I can just step into a country and say, hey, come here. But he managed to get access, and now he's on a mission to sort of replicate this type of work in all of the countries across the world. In the, I guess, in Malaysia, Egypt, you name it. But it's much, much more challenging, right? So having this data, first of all, it needs to exist and properly maintained. And then if it exists, you need to get your hands on it. And a lot of lower income countries will say, it doesn't exist, and even if it exists, they won't give it to you.
But even with the tax data, of course, let's say for Scandinavia, let's say Piketty and Zuckman and also even in Sweden, the top 0.01% has tax evasion rates of 25%.
So even that is still subject, but at least it's a lot better.
Yeah, of course.
4% altogether.
Yeah.
And so I know the reason why I know that the also try this, for example, Egypt, like I've done a fair bit of work with Egypt. And so Piketty's team has tried to do the exact same exercise with Egypt and Egypt has done. And I know for the fact Egypt at some point came to me, the Egypt office in the World Bank. If you look at official estimates of inequality in Egypt, it ranks Egypt as one of the most equal countries. Now, anything you've been to Egypt, you'll know anecdotally that doesn't make a whole lot of sense. And so at some point, they sort of knocked on my door and said, like, what's going on here? Like, why is it that Egypt? This issue that sort of Piketty is trying to address is probably the culprit. And Piketty himself and his team is trying to sort of get his hands. But this tax record data doesn't exist. It simply doesn't exist. It's not collected, it's not digitized, it's just not there. And so he gave up. But I didn't know. So I thought, okay, if it's not tax record data, is there any other sort of secondary data source that we could possibly get our hands on that could stand in for tax record? Some other data set that gives us better information of what the top end of the income distribution might look like, than completely ignoring it. And so what we ended up doing is using house price data. So again, it's a type of data that is the real estate market is very liquid. It's underdeveloped in Egypt compared to say, the US or other countries, but not for the rich. Like house prices for the rich, it's a liquid market. It's very transparent. You can observe it, etc. Not if you want to sell a small house at a low price in the rural part of Egypt. No, you won't. That won't be advertised by. But houses among the rich, that's a very transparent liquid market. And so we managed to get like data for Cairo and Alexandria, where presumably most of the rich live, tens of thousands of house prices. The survey gives you a sense of what the relationship between household income and the price of the house people live in. And so piecing these two together allowed us to get a sense of what the top end of the income distribution might look like. And so it's conceptually very simple, but instead of text record data, we use house price data. And again, it shows we have this massive upward adjustment in the income inequality in Egypt that do compared to official estimates. Anyway, that was a bit of a digression. So poverty mapping at the World Bank in a nutshell. So as I told you, it started in the 1990s with this project in Ecuador by Chris Albers, Pete Lanyang, and Jean Lanyang. And in fact, the original Heskel Hensel was part of the project as well. Got published in 2003, and since then it was an explosion. Like it first, once that paper came out in Ecuador, a lot of countries wanted the single map. Like there was huge demand for it, and within a record amount of time, after Ecuador being the first, it was applied in like 60 countries worldwide. And now I think it's more like 100 countries worldwide. And many countries will have now multiple poverty maps over time, so you can also track poverty at the municipal level across decades. I have a paper with Chris Albers on something I'll talk to you about later on. So the World Bank originally developed its own software, sort of to streamline this whole process, because it, especially the relation became, it was quite laborious, and it was quite computation intensive, because you were dealing with population census data, which are huge data sets. And in those days, computational power was not as strong as it is today. And so putting things in Stata or whatever your software choice was, it was very challenging. Often you had to break up the country into provinces, study one province at a time, glue your software together again. And so that prompted us to develop our own software. And the whole idea of that software was, it was built from scratch to be computationally as efficient as possible. Whatever the computation hardware was at the time, try to manage data, store it in memory in a way that facilitates the managing of big data sets. And it made a huge difference. Like was like X times multitude faster than if you would do this in Stata back in the day. Since then, computers have become a lot faster. And so now the World Bank has developed a new Stata package called SAE, and you can download it for yourself. It's available if you find it SAE, Stata, it should pop up, which is nice. So it's able to handle big data sets now with faster computers. It allows you to script things easier, which is helpful. Scripting was harder in this original sort of software, like mostly user interface driven. Also, recently the World Bank produced what it calls a guidelines document. So in an effort to harmonize, because now poverty maps have been carried out at any given point in time, multiple poverty mapping exercises have been carried out across the world, and we thought it would be very value to try to harmonize this a little bit, so that if somebody makes the effort of compiling all those poverty maps that are done across the world, that it facilitates compatibility across poverty maps. So there's a guideline document. The guideline carries this title. If you're interested, you can put that title in a Google search and would allow you to download that report. Moving forward, this is a closer slide of the first PowerPoint, is so as I indicated, population census data is a precious resource. Also, it is infrequent. Like most countries conduct a population census once every 10 years or so. Okay, so even if you're able to get your hands on it, you can only do this exercise once every 10 years. More often, conducting a census, the typical value chain is statistical office conducts the census, takes an enormous amount of time to process and clean this data. And it's a tall order, right? It's not easy to process millions of observations. So it takes its time to ensure data quality, which can take months, sometimes more than a year. Then you have to secure access to the data, which, for example, in the case of Europe, took us a year just to secure access to the data, sign up the appropriate contracts, etc. Then you have to do the exercise, which in those days would take up half a year. Now it's much faster, but in those days it was so by the time your poverty map comes out, it may be 3 years after the data was already collected, right? So it's almost outdated as of the day you launch your report, right? So it has a lot of strengths, population census data, obviously, but it has some limitations as well. And that has prompted the community, the poverty map community, to also actively look out for alternative sources of data that could conceivably replace the population census. Something that also provides complete coverage of a country, but is more easily accessible and at a higher frequency than a population census. And that's what Akuba is not here now, but we briefly brought up remote sensing data. So that was in its infancy 1 or 2 decades ago, but the amount of data you can extract from satellite images is sort of expanding rapidly by the day, and at low cost. Like there's a lot of covariates that you can sort of get at very low cost. So that's at the moment sort of a field of active research, extracting covariates of local sort of standards of living that can be extracted from satellite images. And then see how good of a document can we extract from this type of data. If we fully replace the census with covariates that can be extracted from that type of data. Then there is active research in model selection. So you mentioned machine learning, for example, and then forest. So I'm personally not convinced. I think the contributions are going to be marginal here, but that doesn't. It's still the case that there's a lot of work here, and there may be countries where the gains might be more substantial, right? So one should be careful to sort of make general statements. Even in many countries that using increasingly more sophisticated model selection sort of approaches might offer marginal gains. There may well be countries where these gains are more substantial. It's an active body of research, and one of my colleagues, David Niemann, at World Bank, is involved in that. And if you're interested in this type of work, I encourage you to look it up. Another area of research, but I'm also personally involved in, is on the use of polymers. So once you produce the polymer, how can you use it in the decision-making context that sort of takes advantage of this type of information? And then finally, small area estimates of welfare, whether it's poverty, inequality, and other areas, could themselves become part of future research, right? Think of like submission of growth regressions or other sort of empirical analysis that sort of when sort of this type of data could become a valuable input. And I'll say a few words about that as well.
I mean, maybe you go into that, but on the first point, the poverty mapping is not a population center, so you only have to survey.
Yeah,
right. And then you can pull from satellite images or whatever.
Yeah.
Material in the like road network.
Somewhat not roof material, but
well.
Yeah. So roof material. Also, I have my next slide. I'm going to dedicate a good chunk of this, but I can say you as a preview. Yes, roof material in principle can be extracted from satellite images, but not from free ones. So satellite image data can broadly be divided into two categories. One that is publicly available satellite imagery, and that's available to anyone, anywhere, at no cost. But there's a type of data that is where the resolution might be, depending on the variable, the resolution might be like a kilometer by kilometer, something like that, right? Half a kilometer, half a kilometer. And so for most covariates, whether it's nighttime lights or greenness or recognizing major road network structures, recognizing urban footprints where the big cities are located, there's a lot of data you can extract from something that has a resolution of a few hundred meters by 300 meters. And it's freely available. Now, in addition to that, you could purchase higher res imagery. But now it's not free, of course. But the higher resolution allows you to extract covariates that you would not be able to extract from public. So covariates, for instance, like rooftop material. You could count cars. You could check the urban planning structures. I mean, there's so many sort of. If you have this high resolution, are literally like meter by meter. So there's so much. There's a rich set of information you can extract out that you cannot. The only downside is this can be expensive, especially in a big country. Like maybe it's one thing if you do something like this in Denmark, but if you want to build a polymer for India, for example, and where these things are priced for sort of square kilometer, it can be a hugely expensive exercise. Any other questions?
But we'll get into this.
I'll get into it. In fact, this was the last slide, I think, on this one. So this is when I had originally envisioned to make a transition, reach the coffee break, but I ended up. So it's not so this second sort of presentation for today, roughly speaking, consists of three parts, three subcomponents, and the using set of activity is the middle one. And then the last part discusses briefly the use of small estimates in regression analysis. Okay, so part one is empirical best prediction. Okay, so just to quickly review, so we assume this standard of linear regression model for, so this is still what we're combining survey with population census, right? So we have this household assumption. I just slightly changed the notation for the subscripts, right? So it's now household H in area A rather than household I in area C. And we have these two errors, location fact UA and this household inferring error epsilon AH. Now, in ELL, we have this massive out of sample prediction exercise, right? Where ELL estimates the distribution of those errors. And then once the unconditional distribution is estimated, they just, when they impute household consumption for every household, they just draw both the location error and the household error from the unconditional distributions. Right? So for those areas that are covered by the survey, it doesn't try to actually estimate location error. And so there is this other stream of literature, most notably in statistics. Well, that's somewhat wasteful. For those areas that are covered by the survey, we should try to estimate location effect and then not draw the location effect from its unconditional distribution, but draw it from a distribution that is being conditioned on whatever data that is observed in that particular area. That literature, however, is assuming normally distributed errors. And I'll show you in a moment. That's because working out that condition distribution is not a straightforward exercise if you're not willing to make any distribution assumptions. Whereas some ELL, they were conscious of this, but they said, okay, we made a choice and it's paid off. We said, in the countries that we've piloted this type of work, we observed that the data was notably non-normal. And getting that wrong will affect you in every area of the country. Right? So the technology that allows you to infer the location effects is only available under the normality distribution. Moreover, there's only bias to something in those areas that are covered by the survey. Now, it so happens that higher income countries, so most of this literature that uses, that does opt for estimated location effects, it's called the empirical best. So it's called empirical best prediction. That was developed with higher income countries in mind. It so happens that in the US, in Europe, and a lot of other income countries, if your area of interest is say district level, a lot of surveys in Europe and US and other high countries, the percentage of surveys that are covered by the percentage of districts that are covered by a survey is rather high. It's not unusual to have 50, 60, 70% of districts covered by the survey. And so in those cases, it makes a lot of sense. You get a lot of violence, right? So because all of those districts, trying to estimate location effects will buy you some position. The lower income countries, so the project was piloted in Ecuador, but this extends to a lot of other lower income countries. That number is much lower. You may only find that 10, 15, 20% of districts are covered by the survey, right? And so trying to estimate location effects will only help you with districts covered. But if that's only 10, 15%, you're only going to get more precise estimates for a minority of districts. Whereas imposing normality, even though the errors show clear deviation from that, it's going to hurt you potentially if all of the districts across the country. So there's a trade-off. So as I said here, so you all believe that sort of that trade-off would be in their favor if they allow for normality, but that was in large part because the countries where they worked on the only like a comparatively small scale of districts were covered by the survey. Okay, so having said that, sort of the statistical literature that was mostly with higher income countries in mind, sort of adopts this empirical based prediction, and this just gives you a very brief overview of what that is, right? So as you can understand, the total error term is this EAH, right? This consists of the sum of the area error and the household specific error. If you observe that total error, which you do, for all the households in, say, area A, and you would compute the average of that error, right, which is going to be UA plus the average of these household-specific error terms of all the households that are sampled in area A. That variable is going to be highly informative of the location effect, right? So you will want a condition on that. And so it so happens that if you're willing to make the normality assumption, if you're willing to assume that the unconditionally, both the area error and the household error are normally distributed, then the conditional distribution of UA conditional on this average residual is also normally distributed. The expected value of this location effect, conditioning the average residual you observe in your survey, is gamma times this EA, where gamma is the ratio of the unconditional variance of the location effect divided by the sum of this location effect plus the variance of the household idiosyncratic error term divided by the number of households in there. Now, if this guy gets really large, right? So suppose you observe like 1,000 households in area A, this guy will go to 0, gamma will go to 1, and so that conditional distribution will get increasingly more tight, and it will go to UA, right? Because if the number of households sampled in area A gets very large, that epsilon bar A goes to 0, right? Because the idiosyncratic error are assumed to be independent across households. So if you average over an increasing larger number of households, that error will just average out. It gets smaller and smaller and smaller as you average over a larger number of households. And so that average residual term will converge towards actual, you will at some point just observe the location effect. Okay? But when this thing is comparatively small, the average residual that you observe is obviously informative in UA, but it is this measurement noise thing, the average household average. Okay, so the variance of the distribution is 1 minus gamma times the unconditional variance of U. So again, you can see that as the number of, either when this variance is low compared to the total variance, or when that number gets higher and higher and higher, gamma will go to 1. So it means that the variance will go to 0. And that UA will eventually go to the average residual you observe. So that conditional distribution will get tighter and tighter and tighter and tighter the more observations, survey observations you have in the area list. Is that clear?
Yeah, I mean, yeah, I guess there's it's a strong assumption still to have that.
Normality is a strong assumption.
Yeah, that IID of because you would assume that particular areas have the errors are correlated across
But
the
the
house.
correlation is even the location thing, right? It's the fact that the total residual has this nested error structure with a shared location effect plus the house error that
Get the house shared.
captures the spatial correlation structure, right? Because it means that all the households that reside in the same location share this location effect. So that is the spatial correlation structure.
Okay.
You can make it more complicated, but you'll see that you only buy so much. You can make it use like a spatial wavelength thing, blah blah blah. Then you're like using a bazooka to kill a mosquito or something. Okay, the question. Something's brewing.
This one, this the gamma A.
So the gamma will vary from area because the number of households sampled on the area will vary.
Config.
Like if any goes, I mean, when you get the variance for U and for epsilon from?
No, you can estimate that. So there are standard methods to estimate. So you observe the total residual, right? And you observe the number of households in each area. And so Henderson method 3, among others, there are a couple of different approaches you can use to estimate the variance of in a nested error. Right? For one, you can easily come up with some moment conditions, right? So you can compute the variance at the household level, right? So this is going to be sigma square U plus sigma square epsilon. You can also evaluate the variance of E bar, right? Which is still the variance of U, but now plus the variance of epsilon divided by number of households. Now we already have 2 moment conditions with 2 parameters to estimate, variance of U and the variance of epsilon. So it's not too difficult to come up with like a moment estimator that will give you estimates of the variance, the unconditional variance of those parameters. Okay, so this is under the normality assumption. Now we were pushed by the European Commission back in the time when they were conscious of this danger to see if we can adopt EB estimation, right? EB, just when I say EB estimation, it just means conditional the distribution for the location effects on whatever survey data we observe for that location, right? But in a non-normal world, right? Because we had sort of convinced them that allowing for normality is important in many countries. But at the same time, especially in countries where a large share of districts are covered by the survey, you will want to employ EB if you can. So the question we had is, can we somehow come up with an EB strategy that relaxes the normality assumption? And getting the distribution right, but this is to motivate that getting the distribution right is key, but I think I've already sort of convinced you of that previously. I'll skip this, it's very technical. Okay, so Chris and I, so that's the 2014 working paper that I referenced sort of earlier on, I think in the previous presentation. We have a project where we try to do exactly this, develop an EB strategy that allows for normality. Now, the original non-parametric approach that was developed EL, it doesn't accommodate them, because basically what they do is they just draw the residuals from the empirical distributions, right? They observe, say, if there's a sample of 10,000 households, they observe 10,000 residuals, and they just draw an equal probability from the empirical residuals that reproduces the non-parametric distribution that you observe, but there's no obvious way of implementing EB. So what we ended up proposing is to fit normal mixtures to the residual data. So I don't know if any of you are familiar with mixed distributions. So a mixed distribution is basically, okay, so let Fx be the density you're interested in. So X is, say, the residual. And we want to estimate the density of the variable X, right? Take up X as residual. X can be written as a linear combination of what we call component distributions. And component, they don't have to be normal, but normal is a convenient assumption, so we're just going to work with normal. And say, let's say we're going to choose 3 components. We're going to say, you know what? The distribution function can be written as a linear combination of these 3 densities. Now what we need to estimate is the mixing probabilities, like what percentage goes to distribution 1, what percentage goes to distribution 2, what percentage goes to component distribution 3. And we need to estimate the first 2 moments, like the mean and the scale parameter for each of the components. And this is exactly what you do. And have you ever done like a kernel density estimation? Like if you open data and you fit the density to like data, right? This is exactly what kernel density does. Like kernel density estimation implements mixture distribution with different choices of component distribution. So in this case, we do normal. You don't have to be normal. It can be something else. It can be, but that's exactly what kernel density does. It's you choose a number of components and you fit this mixture representation to your observed data. And you get what you get back is estimates of these pi 1 up to pi n. If there are 3 components and it's 3, and it will give you estimates for the moments of these component distributions. And so it's very, if you've done kernel density estimation, you will also know that it's very flexible, very powerful. Like you give it data that is reasonably produced. I'm not talking about a density that's like 6 modal, whatever. Like, so give it like a density that is like unimodal, has skewness, kurtosis, you name it. It may have like some bumps, but it is reasonably smoothly distributed. A kernel density can fit almost any density very nicely. And so it's super flexible, right? It's as flexible as you fit your kernel density on your observed data. So this is an alternative way of fitting non-parametrically the densities. However, there's a huge bonus using fitting a normal mixture distribution on data, a la kernel density, than just drawing empirical residual. Because once you fitted a normal mixture to your area errors and also specific errors, now you can implement B. Because it so happens, you can show that if both the area error and the household error follow a normal mixture representation, the conditional distribution of the area log effect, conditional on the average residual you observe in your survey, is also a normal mixture distribution, the parameters of which can be derived from the parameters of the unconditional normal distribution. So this is a lemma in my paper with Chris. This shows you that the probability density function of the area effect UA, conditional on observing the average residual, is also a normal mixing distribution where the mixing probabilities are now alpha I. And these mu i's and sigma i's are the mean and scale parameters of these different mixing, these different component distributions. And then, of course, there is this variable here condition on the average residual. Against the distribution, so it all comes down to now, you observe the empirical residuals, you split it into empirical location effect and household age character. What ELL will do at that point, it will just draw with equal probability from those two empirical distributions. What we would do instead is once we have those empirical residuals, we first fit a normal mixture to that data. It's like doing a kernel density, estimating a kernel density to both of the distributions. Once we have the parameters of that kernel density estimate, now we can work out what the condition is. And now that condition distribution is normal. It can take on any shape. It became slightly more technical than my before the coffee break presentation, but is everybody still with me? With me? You got a bit more quiet. Tobias, are you still with me?
Yeah, I'm still here.
Okay, so you can work out that the conditional expectation takes on that shape over there. I won't bother you with it too much, but you can readily see that if the normal mixture sort of gets reduced to a normal distribution again, which means just one component, you'll get back the same result I showed you earlier. No surprise there. The estimation of normal mixture is very trivial. So I mean, when we developed this years ago, there was no package for it available in Stata. Now there is. It's called FMM. If you want to play with this. And underneath is what is called expectation maximization, or EM algorithm. Some of you may be familiar with. And basically, what it tries to implement is it solves the moment condition that maximum likelihood would do, but it does it iteratively. So basically, if you look, so this is the log likelihood function, right? So you want to find the parameters that sort of set the derivative with respect to the model parameters to 0, right? That's basically what maximum likelihood will do. This equation over here, you can write this equation, this sort of expected value in by first condition on y and then by expected value over y. Now, in maximum likelihood, you would solve this complete sort of simultaneously. What EM does, you know what? It says here we take the expected value over the distribution of y, and then within here are the model parameters we want to solve for. And we're going to say, you know what? For this outer expectation, we're going to work with an initial set of coefficients, model coefficients, right? So those are used to evaluate this outer expectation. We still have the parameters within this inner part here. We're going to solve this moment condition, but now it's an easier moment condition to solve because we split up two things, right? So the parameters we're trying to solve for are no longer here, right? So that simplifies things a little bit, and you'll see it's actually very easy to solve. And then you conditional on, say, theta at iteration k. We solve it, that will give us theta k plus 1. Now the theta k plus 1, we're going to now condition on theta k plus 1. We're going to solve it again. That will give us theta k plus 2. We're going to keep repeating this exercise until theta k and theta k plus 1 are the same. In which case we've arrived at the maximum likelihood solution. And the feature of this, the approach is such that the theta should be removed there, is that the log likelihood value increases with every iteration. Okay, a small simulation exercise, and let me just put this together over the weekend. So if you this is in
One clarification, you started a few slides back, you called this Bayesian.
Empirical base is often a empirical base. empirical best is also, but where you see it from?
Base?
Where?
Or maybe I read it wrongly.
It's the first slide.
Base rules. something.
Yeah, this is a slide that I saw. Where-
Okay.
Yeah, this,
Okay,
this,
this is where base comes.
yeah.
Okay.
And it's also, if you're gonna, the process sometimes is empirical best, sometimes it's empirical base, but they talk about that for the exact same thing. Okay, so hopefully I convince you of the fact that it is possible to marry, because for the longest time this was, as you may not know, it was a fierce competition in these two camps. We had the ELL loyalists who felt like, no, we have to focus on normality at the expense of maybe not being able to sort of get tighter values for the location effects or X% of the economy. Because getting normality wrong is going to bias us everywhere. And then with the other camp, mostly from the statistics, no, EV is hugely important and it's probably a reasonable cost to sort of achieve normality. But now, with this approach, you no longer have to choose sides, we can marry the two by adopting normal mixtures, in which case the distribution 2 is a normal mixture featuring the parameters that readily observed after basically fitting thermal density to the observed residuals. Okay, now we do a small simulation study. And again, I did this over the weekend, so it's rather incomplete, but I just want to give you like a flavor. So we simulate a population census with 100 areas. Think of them as districts. And in the census, there are 1,000 households in each district. The survey samples 25 households at random from each district. The X-betas I borrowed from the first polymetric study that was done in Ecuador 20-something years ago. Okay, so now the distribution of X-beta, the deterministic part, basically comes from empirical data to get a realistic sort of distribution there. The R squared is said to be 50%, 0.5, and the area effect is 25%, so that, which is rather large. It's at the higher end of what you observe in practice, and we're in the process of varying the parameters. It's just that it's rather computationally intensive, so I was only able to do one choice of parameters during the weekend. And we assume a skewed t-distribution for the errors, and we vary the skewness parameter in the simulation exercise. The poverty line corresponds to a headcount poverty rate of approximately 50%, and we implement 500 simulations. Okay, the first thing I'm plotting here is the conditional mean of the location effect plotted against the average residual observed here. And the red line is what you get under the assumption of normal and excluded errors. And the blue line is what you get if you allow for normality. Now, this may seem like a small difference, and in some ways it is, and it may well be the case that we might find bigger gaps in other simulations or other applications. But having said that, bear in mind that the dependent variable is logging out, right? Log consumption. So a 0.05 difference is still 5%. 0.1 is still 10% difference. It's not completely negligible difference, right?
Sorry, the NM is it the normal mixture method that you mentioned, or?
So NM, so the blue line is NM, stands for normal mixture.
Okay.
The MR
Is it,
stands for the initials of the authors that are trying to advocate for the normal EV approach. It's Molina Rao. Sorry, you should have said that. Yeah. So the authors that have been trying to sort of lobby for the normal EV camp, told you with these two camps, ELL camp and the other camp. The other camp is MR. It's Molina Rao and their loyalists. Okay, so what we do here is, so we do 500 simulations every single time. We know the true poverty rates in every area because we simulated the data, right? We implement the poverty rates the same way we did in Brazil and Denmark and Slovenia. That will give us estimates of headcount poverty rates for each small area. And then we can compute the difference. What is the square difference between the true poverty rate and our estimate poverty rate? And then we just compute the mean square error. And then we evaluate the mean square error. Take a look at that. Okay. And what we vary here is a skewness parameter. There's a parameter in the skew t distribution that allows for skewness. And so when this is 0, we're back in the world of normally distributed errors, and so no surprise there that the two approaches sort of overlap. But once we deviate from normality, the two approaches start to diverge in terms of their sort of mean square error properties. And you can see that the root mean square error is lower if you accommodate the non-normality in the data. Any questions on this so far?
The ELL seems to win.
So there's no ELL here. This is just this.
Yeah, but I mean to say the fact that it's stressed are non-normality.
This is non-normality with EB combined. So this is the best of both worlds.
Okay.
So ELL would actually lose. If I would plot ELL here, it is way up there.
It's way up there.
Yeah. So to be fair, this simulation experiment is very much designed in favor of EB, right? Because by construction, 100% areas are part of it. That's their variance. On top of it, we chose a lot of high variance for the location effect. So everything was chosen in a way to favor EB. So it's not completely fair towards ELL, but both beat ELL by a margin. But between the two, so both are now EB, except that one is basically a combination of ELL, basically non-normal and EB. The other one is EB, but incorrectly assuming normally distributed errors. And you can see that, and by varying the skewness parameter, we deliberately introduced normality. And so incorrectly assumed normality results in loss of precision, as the simulation exercise shows. Okay, so that concludes the first part. So now we have no further questions. So this is part. So I try to conclude the last slide, give you a flavor of what is some of the ongoing research in sort of the poverty mapping literature. This is one of them, sort of trying to many different approaches with normality. The second approach that I'm going to discuss now is another active field-to-feature research where people try to replace the population census with remote sensing data. So that's going to be covered next. Another field of active research is going to be the third part here, where we're going to focus on regression analysis using small area estimates, and then there's other. But these are I just selected some areas trying to give you a flavor of some of the ongoing research that's currently. Go ahead.
A general question.
Okay.
So because you talked about the mixture distribution.
Yes.
Something that I think I've heard about, so to say like in general theorem that essentially any distribution can be approximated.
There will be
in a series of any other.
Exactly.
It can be normal, it can be log normal, it can be whatever.
Exactly. There will be theorems that show you exactly that.
Yeah.
That if you increase the number of components and provided the data is replicable, that you can get that it will show you sort of how small you can get the error. And it will go to zero. It can be made arbitrarily small. Yeah. It will get harder if you talk about really funny, like really weird, discontinuous distribution making weird jumps. Still, if you throw enough components at it, it will even get those right. It's that you need increasingly more components. Right? If your density has like a lot of weird nonlinearities, up, down, up, down, up, down, you're going to need more components. More components means you need more data to fit those components, right? So if you have enough data, any density can be fit with normalization. Any. But with the amount of data you typically have at your disposal, you may only be able to fit things with like 3, 4, or 5 components at best, because more components will accommodate. But with that number of components, any risk it can fit perfectly. Like so, anything you can think of, skew T, log normal, gamma, whatever, gumball, you name it, a normal mixture with just 2 or 3 components will fit it very accurately. You have a question, Roy?
No.
Okay, so then we move to part 2, when we replace the census with remote sensing data. So in general, right, so the poverty map approach is all about using a subspatial modeling approach to generate small estimates of welfare by combining household survey data before with the census, the number of processing. The important part being you use a data set that provides you with complete coverage of the country. And both population census and remote sensing data check those boxes. Having said that, you would still expect to get more accurate results with population census data. It's just a much richer set of data, right? Just picture any given country, say the US, right? Population census data will give you detailed data on demographics, on education, on employment, on health for like 300 something million people. Remote sensing data is going to give you fewer characteristics and much less observation. Your unit of observation is now going to be like a square kilometer or something. So in most countries, sort of the population will be the far richer source of data, and so it's expected to give you more precise results. But remote sensing data may still give you, albeit maybe somewhat less precise, but still very estimates at a very acceptable level of precision, and that's something we're going to investigate in the second part. But the obvious advantage being that this data is available in every country, every year. And the every country part is appealing, because like with population census data, you get access to say census data for Malaysia. It's a lot of painstaking work, processing the data, cleaning it, going through the questionnaire, comparing it to survey, blah blah. Now somebody asks me, from Thailand. It goes through the whole process again. It's very laborious. With this, once you have a script, the remote sensing is global. Once you have a script that is set up to extract covariance from certain data, it doesn't matter if you run it from Malaysia or Thailand or Serbia or Holland. It's the same script. So once you have a shapefile, all the remote sensing is completely global. So you can reproduce it for another country is like easily. So it has very obvious advantages. The only question now being, how accurate of a map can we get with this data that is so convenient in so many ways? So this is just to give you a sense of some of the covariance. So nighttime lights is something you all have heard of, which has become very popular. I think there were some CDR papers back in the day that showed that it correlates very well with national GDP data, etc., as well as with some national GDP data. But so that was one of the first examples of remote sensing data that was used in economics. But by now, it is land coverage, it's population density, it's recognition of major road networks, location of populated areas, greenness, climate data, pollution data, slope data, ruggedness data. You name, there's so many covariates now that can be extracted from publicly available data. Now, if you have a little bit of money available, you can buy high resolution images, in which case you can also start counting cars, recognizing stock materials, etc., etc. So that is, and this is a very rapidly developing field. Now, whatever you think you can construct today, check in next year, and there will be another set of variables that you can extract from. It's a very rapidly evolving, and at low cost. So in this project, so the idea of this project was, it's a project of Malawi, and the idea being that what we want to do is we want to test. So if you do a smaller Google search on the use of remote sensing data to map poverty, you'll find lots of papers. So it's really active field. But what most of the studies do is they take a survey, combine it with remote sensing, and produce a poverty map with little validation. Yeah. Right? So it doesn't tell you how good of a map compared to something. So what we try to do here is we pick a country, in this case Malawi. We built a poverty map using the ELL approach, using what we think is the richest possible data set you could use to build a poverty map. Then we ignore the population census entirely. We do a whole new poverty mapping exercise where we combine the same survey now with remote sensing data, and then we start comparing the two maps and see sort of how good of a job can we do by replacing the census with remote sensing data. That's the sort of the idea of this project in a nutshell. Okay, so that's the question that was listed here at the bottom.
And why are you still using the ELL method? Why not the other assumptions?
So the short answer to your question is when this project sort of got started, it preceded my other project, which is on the, so that could be legacy. Yeah, it's a good point. Yeah, it was a secret. Okay, so in a nutshell, so now the unit of observation is no longer the house, right? The unit of observation is
The
a village. Think of it as a village, a location. That also brings us to a data requirement. So the survey, the household income survey you're going to work with, it needs to have geocoordinates on the primary assembly units. Now there was a poll order 50 years ago. Today, almost every household income and household consumption survey will record the geocoordinates of its primary assembly unit. So it's not really much of a requirement anymore. But you still need them to share it. So collecting is one thing, sharing is a whole separate issue, as you are all very familiar with. Yeah. Okay, so now unit check. So we have the regressors, I call it Z now. So the regressors are converged, it can be extracted from the remote sensing data. Beta is that our rotation coefficients, and U is now the error term. But we're going to invest a little bit more effort in capturing the spatial correlation structure, rather than simple nested error structure. The idea being was, so I haven't tested how much of a difference it makes. It may well be micro. The idea was that since the remote sensing data allows for a somewhat more economic set of covariance and the data, a small number of observations, then we would have, had we used population sensor data, that the errors are expected to be a little bit larger and potentially have more structure in them. We felt like it might be worth the effort of trying to extract as much of the spatial correlation structure out there by adopting a slightly more sophisticated spatial error model. So we use a spatial lag model. I don't know if you're familiar. So W in this case is a spatial weight matrix. I don't know, are any of you familiar with spatial weight matrix? Or is this completely new to you? Okay. No, it's new. No. So, okay, it's going to be hard to maybe explain this in a nutshell, but basically, the spatial, so rho is a spatial sort of correlation coefficient, and W is, so W basically captures the distance between locations. I'm just going to try to explain the conception. So just picture like a big matrix where all the locations are entries in the matrix. So if you have, say, 1,000 locations, 1,000 sort of enumeration areas in the country, it's going to be 1,000 by 1,000 matrix. And the elements of that spatial weight matrix capture distances. And distances can be measured however you want. It can be literal geographic distance, like bird flight, road network, it can be economic distance. There's some flexibility there. Okay, so but it measures distances. And the idea being that locations that are close together are more likely to be spatially correlated than locations further away. So the weight matrix captures that way. The rho, the whole matrix then gets multiplied with a spatial correlations rho. And that's something that's estimated. So this distance matrix is simply computed, right? You just know what all the distances are across the rho gets then estimated. So it says, okay, this is the spatial distance structure. Now estimate rho. And rho basically dials up or dials down the spatial correlation structure. So if you estimate rho to be 0, it just means that there's not much spatial correlation structure presence in your data. If rho is found to be significantly different from 0, it tells you, hey, there is significant spatial correlation structure. That is like in a nutshell, or conceptually, what spatial mathematics is all about.
Do not assume any spatial autoregression. Okay.
This is exactly spatial autoregression.
This just assumes that the error terms are correlated, right?
You mean
You also have that essentially the dependence.
Sure,
is
yeah.
like AR1 or AR.
Yeah, so it's the same thing, but you apply the same concept to the dependent variable. You mean.
Exactly.
Yeah.
Exactly.
No, it's
But I mean that. Yeah, but that adds some.
Yeah.
It's significant additional.
Yeah, it makes it also, and it also makes things computationally a little bit more challenging, which we discovered. So that's why it's not without cost, unless you want to work with sparse spatial weight matrix. Because if it's not sparse, and you have a country where you have, say, in the case of Malawi, we have 12,000 by 12,000 enumerated areas. When you try to estimate the model and sort of work out the critical best conditions, you have to do matrix calculus, including inverted matrices, computing eigenvalues of 12,000 by 12,000 matrices, which is not a trivial task. Anyway, but I'm not going to bore you with that. So Z are sort of the covariates that can be extracted from and we're going to assume normally discrete errors in this case. Any questions so far?
And the choice of the predictors that now you're thinking about that we want to choose from this remote sensing data is basically you're throwing in everything you have available.
Yeah, so typically what people, same as population. You're trying to be, you don't like to be restrictive beforehand.
Yeah.
Whatever you can get your hands on, whatever you think might plausibly be correlated with local standards of living.
Yeah.
And then you adopt model selection criteria to help you sort of identify what the appropriate covariance is. That should be part of the model. Yeah. Any other questions so far? No? Okay. So it's an application to Malawi where we have a little over 12,000. Coincidentally, we have 12,000 households. We also have 12,000 populated areas.
Wow.
That pure coincidence. See? Wow. I'm only noticing that now. So it's a household survey that covers a little over 12,000 households in 767 primary assembly units, about 16 households per PSU. And there are 31 districts, and every district has a minimum and some much more than 24 PSUs. The population census covers 30 million individuals in 3 million households, so there's a million missing there. Again, over about a little over 12,000 enumeration areas. It's that number that can make the matrix algebra computation challenging. Oh yeah, you also need shape files, by the way. So I mentioned the remote sensing data is freely available, but the remote sensing data comes in grid form. So it literally is grid by X, half a kilometer, half kilometer, or 100 megabytes, depending on the covariance. If you want to extract, overlay things, compute things from your primary sample units or the numeric, you need a shape file that you overlay with the grid. That now allows you to extract what the random lines, what the greenness, what the ruggedness, what the slopes, are for that particular primary sample unit and numeric in the country. So that is a requirement. You need shape files that that geo-reference the PSUs in Malaysia actually in country. And ideally obviously also the small area boundaries that relate to it. So that is, these are the two things you need. The primary sample units in survey need to be geo-reference, and you need to have a shape file that geo-reference the enumeration areas in your country. Okay, this is just to give you a feel of data. So these are these 767 primary sample units put on the map in Malawi, and the color indicates the poverty rate that is observed. As in every primary sample unit, we have something like 25 households, if I'm not mistaken. So 16 households for the PSU. It varies a little bit, but by and large it's 16. And that allows us to compute for every PSU what the poverty rate is in that particular primary sample unit. And that's what the color indicates. Here is just some tables that gives you, if you want to glance it, this gives you a rough sense of some of the covariates we're working with that can be extracted from remote sensing data. So this is to the capital, this is the border, elevation data, population density, all kinds of agricultural variables, climate variables, temperature, rainfall, potential evaporation is also a climate variable, pollution data, greenness, ruggedness, nighttime lights, population counts, travel time to major cities of different sizes. There's a lot. All of this is freely available. Everything. So, but the whole idea of the project was how far can we get with covariates that are available in the public domain, so that this type of project can, with the flip of a finger, apply it in another country of interest. And so it's provided with a lower limit. Like if you're willing to spend money on higher resolution imaging, the result will get better.
So how granular would each?
That will, the granularity is limited to the cost. So it will vary. For some covariates it's 1 kilometer by 1 kilometer, others is 300 meters by 300 meters. So the granularity will vary from imagery to imagery.
But I would probably like one certain from one observation, I think we're very variable. I could have like paved road within.
Sure, yeah.
Meters within.
Exactly.
Kilometers.
Exactly.
Because
Exactly.
paved road, I would want to create a number of different.
Exactly. Exactly. Yeah, exactly. You know?
And now we have to run the flex working.
So here are just a few maps to give you a sense of what these covariates look like. So this is agricultural opportunity cost. A lot of oftentimes those variables, you know, a lot of the pre-processing work is done by us. So all these layers, the raw data are available in the public domain, and then you'll have scholars in various domains, agricultural experts, climate experts, trade experts, that take in the raw data and extract a bunch of covariates from it that you can then readily sort of use. So a lot of the work oftentimes is done by others that we can sort of take advantage of that. So for example, agricultural because is an example of that. This team sort of takes the raw data and computes a variety of agricultural variables that you can then sort of take in temperature data, standard deviation about seasonality within the country. This is to major river, forest cover loss, landscape population totals, and then often even for a particular variable, also oftentimes have like competing variables that are maybe like more than one team. In the case of population density, it's like half a dozen teams that sort of work the same, so you can have competing sort of data on population locations. Log of nighttime lights at various times. You can also include these things. You can sort of hold it today. You have liberty to model that as nighttime was today, nighttime was 5 years ago, 10 years ago. You can include legs of the various variables as well in your model. Ruggedness means slow. Travel time to a city that is at least 50,000 people or larger. Vegetation is like greenness measure. Share of rain-fed crops, etc., etc. So I just put it quickly a sample of not all of them, and then this is what the regression model looked like. This was at the time. We have since, just for information, in case you're interested, a lot of the papers that I've presented, so some of that you can download, but those versions that we're now are outdated. I've been working on them since then. If you're interested in any of them, the best thing is to just shoot an email, and I will share with you the latest version of whatever paper you might be interested in. This is an example of that. So this is from the, I think from the working paper version. We've been working on it ever since, and we've made updates, the modeling part, etc. So the estimates for this will be slightly different from what I'm reporting here. What is there to say? Well, I mean, a lot of things make sense, right? So, for example, nighttime lights, higher levels of nighttime lights means lower poverty rates, greater distance to the city means higher poverty rates. So, a lot of these covariates sort of make sense. Unit of observation is 767, right? So, it's going to be notably smaller, better than mine, than if you would have done a similar exercise. When you combine certain population census, it's not just that the census is being replaced with, in this case, more census data. It also has implications for the data you have available to train the model, right? Because now we have to train a model at the PSU level. In this case, it means we have to train a model using 767 observations. But as if we were combining it with a population census, the model will be at the household level. In which case, we have over 12,000 observations to train a model. Is just sort of a practical detail to keep in mind.
But if you had offer coordinates, then you could do those.
We'll talk about that. Yeah, that's.
I know.
Yes, but that doesn't exist. Yeah. Plus, even if it would exist, a lot of the right-hand side variables don't vary at that level of granularity. So in effect, it's still as if you're collapsing data at the PSU level. But there's not your access don't vary at that scale.
And we have something like 15, we have like 3 minutes left. I think everyone is.
Okay, so what I'll do,
15 minutes over time.
and also we started missing some of the. So what I'll do is I'll wrap up this component, and then the third component that I scheduled, I'll just start tomorrow with that third component. It's a relatively short component, so we're pretty much on schedule. So what we try to do here is show you. We were just trying to get a sense of how much mileage we might be able to get from investing more in the spatial correlation structure, remember? Because we thought, okay, we have less data to work with for the model training and a more modest set of covariates, so we thought it might be we could get more mileage of investing into a more sophisticated spatial correlation model. So what we did here is we show, so what we do, we implement the exercise, we compute poverty out of sample, and then we correlate it with the true population observed in the survey for those 767 locations, and we just compute the correlation. The correspondence between the observed poverty rate in the survey versus the predicted poverty rate in our model. And then we vary that here with the coefficient that captures the spatial correlation structure, right? And at some point, you expect it to peak around the true spatial correlation. This is the rho parameter that I introduced to you a few slides back. And the numbers that you see, 1, 2, 3, etc., is the number of covariates in the model. So the full model is 15 covariates. But what we did, we deliberately, incrementally stripped it of covariates. Right? We went from 15 to 11, from 11 to 6, etc., all the way up to 1. And so, as you economize the model, obviously the error term will become larger. And you would expect you're going to get more mileage out of calculating the spatial correlation. And that's more or less what you see, right? So, if you just have one covariate, first of all, you see there's a huge gap between simple OLS model that fully ignores the spatial correlation structure and having a spatial autocorrelation model, right? That tries to squeeze the structure that is left in the residues. Okay, so we get a much bigger fit. If you just have one covariate, you get a lot of mileage adopting this more sophisticated spatial autocorrelation model. But as we start to add covariates to the model, that gap becomes smaller, 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 and smaller. And so at some point, you're going to reach a point where maybe that the risk that you made on this much more sophisticated spatial autocorrelation structure will give you a marginal return. Now, this picture may vary. This is Malawi. If you would repeat this exercise in a completely different country, you may well find that this gap is still notable. Any questions on that?
Seems a little frustrating that, you want to save time instead of doing all this special work on spatial correlation and OLS.
Yeah, I thought this was disappointing. I was hoping to
Yeah.
see
But you only know it after you.
Exactly. Yeah, after it cost us many weeks of my life. Yeah. But it's results, and hopefully it will prevent others from losing valuable weeks.
But that's the thing, it's different for each country, right?
That's true. But it gives you some intelligence, right? So you're making an educated guess one way or the other. Next time somebody else takes on this type of exercise. But you do it, and while we do it in another country, you will make it political still. But I think at some point, if like 5 people go through this work, and 5 times we get the same result, then I think the 6th person can safely sort of so here, what we do is we plot this is the ELL, so the poverty estimates at the district level obtained using ELL, and this is the poverty estimates obtained using remote sensing data. Before I show you this figure, I show you down now. Let me first show you this figure. This is the poverty maps obtained. So this is the poverty map obtained using ELL, and this is the poverty map obtained using the remote sensing data. And I think similar to sort of when we did the validation of ELL, where I showed you for Denmark and Brazil and Slovenia, if you just look at the geography, they are remarkably similar. So I think that it does a reasonably good job in capturing the geography of poverty. So that's one of the conclusions from my exercise. If you're interested in like general patterns of poverty, right, the document is helped by getting a sense of the geography of poverty is helped. If you're interested in individual districts, estimates can deviate substantially. So if the decision maker is like there's 1 or 2 districts, right? There's a potential policy intervention and needs to know what happens in this 1 or 2 districts that are part of the program. Estimates can deviate substantially. If you're interested in broad geography, which involve a much larger set of districts, so it captures the geography quite well. That's sort of I think the overarching conclusion that we hope to replicate in other countries, but based on my experience in this country, geography is well captured, but estimates from every one individual district, estimates can be off substantially.
But the ELL seems to be more regular. be a little bit more.
Maybe a little bit more.
Like, on the left, you have the areas, in the bigger areas, for color.
For example, here, like email, you're able to pick up differences here.
Yeah,
For example, which are unable to pick up here.
yeah, exactly.
Yeah.
Yeah,
So there are differences for individual neighboring places. But if you take a step back and you just look at the overall sort of general geographic patterns, I think the approach does a good job. And if that's something that the policymaker will be helping, I think job well done. But if you're interested in like comparing two specific districts, you can get markedly different results. That is sort of the general conclusion we try from this.
have you tried to combine the two, see if there is any mileage over the
So, yeah, so to the extent that what we have done, and also as part of this exercise, is those covariates that are that we use as predictors in the sort of remote sensing exercise, include them as right-hand side variables in the model of ELL. And what you'll see is that if you just include them, obviously they're highly significant. But once you start including the type of covariate that you observe that are shared between the census and the survey, demographics, education, and so on, they all end up being easy. Like they get overpowered by the variation you observe in population census. Again, that's in the implication allowing. Even well, I wouldn't allow if you visit another country that conclusion too might change. But based on this experience alone, allowed, that's what we found.
Hear me? Sorry, this is Steve
Yes.
remotely. Oh, great. Hi, I'm Steve. I'm based in Amman, Jordan, with the Yemen poverty team, and this is really interesting. So thanks for this session. I suppose I got a quick question about obviously in Yemen, it's not possible to have censuses for quite a while, probably back to 2014. So this kind of remote kind of monitoring is very interesting. We're starting to investigate it. So I don't really have a specific question as much for now, but we're just wondering whether you've worked on the Yemen context at all, and also any further kind of detail, maybe separately on this kind of remote sensing would be really interesting, because we're obviously very limited on the amount of data we can collect at the moment. So yeah, thanks a lot.
But let me just say this is so Steve, are you with the World Bank? Did I understand correctly?
Yeah. So I work with the poverty team with the World Bank.
Okay. So coincidentally, it was I think like a year ago or give or take. I think someone approached me from the World Bank who asked me if who expressed an interest in building a poverty map for Yemen using remote sensing data. And then the project never came off the ground for reasons I don't quite recall.
Yeah.
But yeah, in principle, I see no. If there is a survey, a recent survey for Yemen, where the primary sample units are geo-referenced, in principle, there's no reason why this cannot be done for Yemen.
Yeah, I think we're going to be building on some of that work that was carried out. So I think it's Jean-Luc Amele who reached out. So he's now moved team, but we're kind of picking up on that work, and we're also hopefully working with the Office of National Statistics a little bit to try and re-establish that. So there's a number of things going on, including potentially a small household survey. But yeah, I think this is going to be starting to kick off a little bit more in the next few months or so. So I think that's going to come.
So if it helps, you should feel free to reach out to me at any point. If the help you anyway.
I will do.
I mean, you have my
Yeah, I
email
will do.
address. Yeah.
Thanks very much.
Any other questions before we continue tomorrow? Everyone still okay with my pace? Second part was slightly more technical than the first part, but pace is still okay?
Yes.
Okay. Good. I hope you enjoyed it. Hope to see you again tomorrow.
Just be quick, when are there no questions in the audience? Then is there anyone else online who would like to ask a question? You can just raise your voice, speak out. Then we have one of them for each day. Yeah, then
Apart
please,
from
you have the QR code, please scan it and fill out the very quick survey. Do we have a QR code for the online people?
We shared them a link.
Okay, and if you've done it online, on the link, but also, I mean, there's a link to the survey directly. Please fill out the survey. It's literally 5 questions. It takes 20 seconds at most, but of great value to us. So please do that. And other than that, so I think it was a great first day. Tomorrow more to come. We convene here again, same time, same place, 1:30 tomorrow. And if you joined us online, you should also have the link for the session tomorrow. So thank you very much. And let us give Roy a hand.